Good to see you here. Okay, we're going to start the second day now. I just wanted to let you know that if you need to have discussions with other developers, there is a second separate meeting room that is on the 6th floor. And if you go to the elevator, which is next to the coffee place, you, all the instructions are there basically. And when you do get to the 6th floor, then you'll have, arrows to lead you to the place. So this is, mostly relevant to the people we're going to talk about memory allocation issue. Okay, well, Jason, here you go.
All right, good morning and welcome. So today I'm going to talk a little bit about what I call the anatomy of a Vulkan driver. So there are, most of us in this room are at least somewhat familiar with GL. Some people have looked at the Vulkan spec. Most of us have not actually worked on a Vulkan driver, although there are now 2 open source ones. So I'm just going to talk a little bit about the driver that we released in February and crack it open and see what's inside. Let's see here, why is this not working? Okay. All right, we'll try this. So first we'll start off with the obligatory brag slide. I do think we have a little bit of bragging to do. Okay, this is not working. I guess I need to click. So between May 8th and February, some of us, particularly me, Christian, and Chad, and a couple of other people helped out as well, wrote a Vulkan driver. Specifically, we wrote a brand new from-scratch driver. It's not entirely from scratch. We did use the backend compiler. That's a little bit of the driver. And we used No. But everything else, state setup code, surface layout, all the front-end compiler bits is brand new. It's a brand new API. Everything was massively in flux. Most of the time we were writing it. The spec would change on a daily basis, and we had to continuously roll things forward and keep going. So that presented some interesting challenges. We did it with about 3.5 people. That's on average. Predominantly it was me, Christian, and Chad, although there were times when one of us was off doing something else, and there were some other people that helped out, especially later on. We did it in 8 months. So we actually started working on our driver after most of the rest of the industry was demoing theirs at XDC. We had a tiny little kind of a prototype from an ancient version of the API that Christian had hacked together in a week, but that's all we had done. We were conformant on day 1, which is also something that not everybody in the industry is able to say. When the spec was released, there were 5 implementations across 4 hardware vendors that were actually conformant, and we were one of them. And we were open source on day 1. So the day the Vulkan spec was released, once all of the obligatory, everybody got to release their stuff before us happened, we sent a mailing list mail to Mesa Dev and pushed a branch, and there it was. We also did something interesting with this that we hadn't really done before, and that is we were actually working open source before the spec was released. Open source. Because of the way Khronos works, everything was under a big giant Khronos NDA. But it turns out there are a whole lot of people who have signed the Khronos NDA. And we wanted to do things as open as we could, so we pushed the driver to a GitHub repository that was accessible to anybody who had access to the spec. And we did it as open source as possible. And it worked fairly well. We actually got a few external contributions from Daniel Stone has a few patches in there that date to before the spec release, and there's a few other people who do as well. So there's my break slide. I also want to thank a few people. It was a very big effort, and especially big thanks to Christian and Chad. We had a lot of fun. It was a lot of work, but we got it done. Christian, Chad, and I were sort of the core team. Jordan joined us in about October. He had just finished getting compute shaders set up for GLES 3.1, and so he did a bunch of the compute-related stuff, including the pipeline setup and some of the compiler work. Manly joined us a little bit later. He got compressed textures hooked up, and he's also sort of been my right-hand man ever since. He's been doing a lot of good stuff. He's been fixing Haswell bugs. He's been working on surface state stuff. He's just been faithfully chugging along. Mark and Dylan did a lot of work as well. I don't think we could have practically gotten conformant without them. Mark has been working like crazy on our CI system, and Dylan has worked a lot on getting Piglet so it can run various DEQP things and enabling us to actually run the test suite on reasonably quickly so that we could test things. There's a bunch of other people in here. Connor did some of the Spurvy to No work. Ken did some compiler stuff. Anuj did some multi-sampling stuff and also some bug fixing, and the list goes on. I also want to mention the Igalia team, who a bunch of them are here today. At the time, they didn't know we were working on a Vulkan driver, but they were working on a VEC4 backend for NER, and that work enabled us to do a bunch of compiler refactoring that made the Vulkan driver possible. So they also go on that list. Oh, and they also did a bunch of stuff with SSBOs. So good work, guys. Okay, so next is a few slides that I copied and pasted from my FOSDEM talk, just to give a little bit of an introduction to Vulkan. So Vulkan is a new industry standard API from Khronos. Khronos is the same group that does, oh goodness, I need to get, whatever. Khronos is the industry group that maintains OpenGL, OpenCL, Open, all sorts of other things. OpenMax, various other things a lot of people don't care about. But Vulkan is the new next generation API that has been released. So it's been redesigned from the ground up. It is not just OpenGL++. OpenGL has been extended for a long time. This is basically a complete rewrite. It's designed for more modern software, more modern GPUs. And it is designed to run on anything that can ship GLES 3.1. So compute shaders are required, so that's kind of sets the lower bar. But basically anything that can do compute geometry, vertex, and fragment is sufficient for running Vulkan. So why do we need a new 3D API? So OpenGL was released by SGI in 1992. That's not as old as X, but it's still pretty ancient. And a lot has happened since 1992. It was based on the proprietary IrisGL API. Mesa dates back to 1993. It didn't take very long at all for that to initially get released as a software implementation of OpenGL. But computers have changed a lot in the last 24 years, particularly in graphics. GPUs are more powerful and flexible. Memory has gotten faster, more plentiful, and cheaper. And multi-core is now a thing. Back in 1992, you didn't have a multi-core workstation unless you paid a lot of money and were planning to use it for doing like 3D rendering or something. Nowadays, your phone is multi-core, and everything is multi-threaded everywhere. But OpenGL has done amazingly well over the last 24 years. It's really very impressive how well the API is done in terms of updating to more modern hardware, more modern programming. And I am going to ask you to give me a second because this Google Drive presenter view is driving me nuts. And I just lost my internet connection, which is awesome. All right, we're going to do this the old-fashioned way and use a PDF. Okay, hide API is still not working in No Shell. we'll just do it this way. Okay. Next. Oh. Can I get right and left? No. All right. Well, whatever. Hide API doesn't work in X either. Hide DPI. Well, exactly. All right. Where's Jonas? He needs to fix my high DPI. All right. So after 1992, so there's a lot of changes. Multi-threading is commonplace. The state machine singleton model that OpenGL uses is not multi-thread friendly at all. When the way you upload textures is to bind it to a singleton context and then make another call on the singleton context, that doesn't multi-thread. Off-screen rendering is a thing. Back in 1992, you did not have enough video memory to have a back buffer, much less off-screen rendering. And so nowadays, you've got 4 gigs of RAM and no big deal. GPU hardware has gotten a lot more standardized. So OpenGL liked to hide absolutely everything. You didn't even know how many bits were in your texture. It might be, 11 bits of red and 10 bits of green and 3 bits of yellow, for all you knew. But things have gotten a lot more standardized. We have compressed texture formats. We have standardized uncompressed texture formats. And developers don't want you to hide everything. Developers want to be able to give you a big giant blob of data and say, this is my texture, this is the format it's in, go with texture from it. And so the data hiding that OpenGL did is not really needed. So Vulkan takes a little bit of a different approach. It's sort of an object-oriented API where you have really 4 objects, the instance device queue, and physical device, there we go, that are sort of singletons that you have to protect from threading. But the rest of the API is entirely object-oriented and reentrant as long as you call it on separate objects and separate threads. And so all of your state concepts, you still have sort of a state machine, but it's entirely restricted to this command buffer, and you can have multiple command buffers and they have separate views of the state, and it just sort of resets at the top of each one. It's also a lot more explicit about what the GPU is doing. Texture formats, memory management, synchronization, all of that is pushed off to the client. The client has a lot of visibility into what's going on. It's still generalized enough that you can ship it on different platforms with different hardware underneath that works a little bit differently. I mean, it does work on immediate mode renders, it does work on tilers, it does work on, whatever. But as much as possible when things are standardized, we try to push some of the complexity onto the client, partly because it makes the driver simpler and lighter, and partly because it's simply necessary when it comes to multi-threading. Because if you're building command buffers in 2 different threads, and I have a texture over here that I'm texturing from and I'm rendering to it over here, I don't know which one of those command buffers is going to get submitted to the GPU first, so the client really has to give me the synchronization information. I can't make it all implied. Whereas with GL, you have a single thread, everything's immediate mode, you just step through it, and so you can do all of that magic in the driver, and you can't really in a multi-threaded scenario. One of the other things that's different about Vulkan is that Vulkan drivers do no error checking. If you do something wrong, you get shot in the head, and that's the end of it. In order to solve that problem, there is a set of open source vendor-neutral validation layers that sit between your application and the driver and do all of the standard checkings that we would do in Mesa main today. But it's centralized in that one place, and then when you actually run in a production environment, you pull that layer out and you do not have to burn CPU overhead validating everything. One of the big complaints about OpenGL that application developers have had is, why am I burning 10% of my CPU validating my GL calls when I don't make a single error in my entire application? And the answer is no good reason. There is a GL extension floating around somewhere that allows the application to tell the driver, I know what I'm doing, trust me. And the driver supposedly turns off validation. But Vulkan also goes a little bit further than that in that it requires the application to pass in more information in certain places so that it doesn't have to do as much tracking. And even with that extension, Vulkan is still going to be a lower overhead API. Okay, so I'm actually going to pull up Terminal and look at some code, because that's where things get interesting. So let me... All right. All right. So I want to talk spend most of my time today talking about how our Vulkan driver is different from our GL driver. So let's start by looking at command draw. I'm going to see if I can zoom this out a little bit to get it all on the page. Okay, so few things to talk about first of all. So this command draw function that we have defined here, the first thing to note is that when the client calls vkcmd draw, they have either asked for a function pointer from our driver and are calling it directly, or they're calling it into the loader, which provides some of the dispatching for them. And where do they go? They go right there. There is no Vulkan main to a DD table, to Gallium, to another DD table, to your driver, to atoms, to state. They call command draw, they go there. The distance between the API and our driver is paper thin. And this helps reduce a lot of the CPU. It also makes it a lot more obvious what's going on. Vulkan's a lot more explicit, and the information we get from the client in Vulkan is fairly similar to the information we get from Mesa main after it's been translated from all of the GL stuff. Another thing is not only is there a very short distance from the API to our driver, there's also a very short distance from this entry point to the actual hardware batch buffer that we're writing packets into. This block here, which I'll explain into a little bit, that emits a 3D primitive call, is actually putting data into a BO that gets sent to the GPU to render. So the distance between your application and the batch buffer is one function call. There is no TNL layer, there is no VBO layer, it's just, there it is. So what does this function do? The first thing it does is it flushes state, then it deals with base vertex because that's annoying, and then it emits the packet. So the way state is handled, the Vulkan API tries very hard to make sure that you can, as much as possible, emit directly into your batch buffer. But unfortunately, because of the way hardware works, you have different bits of state that all get crammed into the same packet. And so you have to have some sort of a process of writing it down and then gathering it up as you need. And that's what this flush state function does. So we do some vertex buffer setup, which I'm not going to go into real detailed. But then most of the rest of it is, are descriptors sturdy, flush those. Is push constant sturdy, flush those, etc., etc. Where the state actually gets set is these command set, like command set viewport, command set Caesar, etc. And these just store it off into a spot, flag a dirty bit, and we emit it later. It's not terribly different from the way that we do OpenGL and Gallium state tracking today. It's just a lot fewer layers. And one of the other differences between Vulkan and OpenGL is that where in OpenGL, almost every single int and float in the entire state machine is independently referenceable and independently settable and has to have dirty bits to track it all. In Vulkan, there are somewhere on the order of 12 distinct pieces of dynamic state. And that's it. So all of our state tracking is in a single 32-bit bit field, and it tracks it with perfect granularity. So while there is some state tracking, it is not nearly as bad as it was in the land of GL. All right, we'll come back to command draw. Something else that we did differently in the Vulkan driver is that we started using XML-generated packing stuff. And this was developed by Christian fairly early on, and we have really liked the way it's worked out. It's one of the sort of improvements to our entire driver stack that came out of this project. One of the fun things about writing a completely new driver is you get to ask questions like, if we'd never written this driver before and we're going to write the driver from scratch based on all of the things that we know today, how would we do that? And it's a fantastic opportunity to go clean things up and do things better. And one of the things we did better is these packing structures. So what we have is we have an XML file that describes where each of the packets lays out in the hardware, not terribly different from the Nouveau stuff that they have. I don't remember what it's called. The format's a little bit different just because we have slightly different requirements, but it's the same basic concept. And then what we have is we have a set of header files that gets generated via a Python script. And it declares two things. It declares a structure which has floats, uint32s, bools, and things in it. One for each field in the structure, and then it has a function that takes that structure and does a bunch of validation and packs it into the actual number of bytes that you need to put in the hardware packet. There's a number of reasons why this has been really nice. One is the syntax is amazing. So if I want to emit a 3D primitive command, I just say batch emit 3D primitive. This amp batch emit macro uses a for loop to give us the nice braces syntax, which indents beautifully in Emacs and Vim. And provides this very, very readable thing where I just say, I want vertex address type, here it is. And it's very declarative. You can very visually see what's going on. What we had before involved a lot of pound defines and ordering things together, and it was not incredibly clear. But this is beautifully clear. And it also does a bunch of validation for us. So if you have a field that's 14 bits and you try to insert something that's bigger than will fit in 14 bits, it will assert on you. It also does floating point to fixed point conversions for us. So if there's a field in the hardware that's specified in 8.4 fixed point, we just have a float in the packet, you stick a float value in there, and it will do the conversion. There's another thing that we hooked up that is my fault, and that is that it will also do Valgrind validation. So if you compile the driver against Valgrind and you are running under Valgrind, and you ever put any undefined value in a state packet ever, it will tell you exactly which one you put in there and where it came from, which is absolutely fantastic for hunting down bugs. That has saved me far more time than it cost. And it just nicely, declaratively emits it into the buffer. One of the other things you'll see here is there's a few instances of, wrong direction. There we go. There's a couple of these genx macros, and what those do is they prefix whatever they wrap in gen 7 or gen 8 underscore. And the capitalized one does it in all caps, and the underscore one does it, the lowercase one does it lowercase. So what we do is, for each hardware generation, we have a different set of packing structures, and a different, which might lay out the data a little bit differently. They might actually have different fields. And we have this one file that we compile 4 times. Once for Ivy Bridge, once for Haswell, once for Broadwell, once for Skylake. And what this means is a couple of things. One is it allows us to use these packing structures, which we generate on a per gen basis, without having to have the packing structures do a bunch of checks to figure out where to put the bits. It also means that when something moves around, we don't have to start a new file and keep hand coding, because before there were places where we had started a new file for a new hardware generation just because they moved something from DWORD 7 to DWORD 8. And it was annoying to try and deal with it in the old file, so we just started a new one. This deals with it for us. One other thing I didn't mention about the packing structures is they handle relocations automatically. So before we had to manually say, put in a relocation here, put in a relocation here. With this guy, it has a address structure, which is a buffer and an offset, and in the DRI driver, we also have gem domains. And there's a little relocation hook, and anytime there's an address, it just automatically does the relocation for you right there on the spot. And so you never have to think about did I remember the relocation? Is this a 64-bit relocation or a 32-bit relocation? It just does it for you. So by using these guys, it allows us to sort of generalize things a lot more because we can have a single piece of code, you compile it on multiple generations, and even though the hardware packets completely rearrange, it continues to pack it correctly for us. It also means that when you call VKCMD draw, you get landed in, let's say you're on a Skylake, you get landed in the Skylake implementation of VKCMD draw. And there is not a and assuming you have a completely empty pipeline, I think the driver will do something along the lines of 4 hardware version checks in the entire flush out the pipeline and emit the draw call. This is to be compared with the GL driver, which first it goes to an atoms table that has a list of big giant things and it calls a bunch of function pointers. There's a list of indirection. And then inside of each one of those, they're usually just littered with hardware generation checks because of different features here and different features there. In this, all of that is compiled away, and when you call the Gen 9 version, you get Gen 9 code all the way through, and it's fantastic. So these have worked out really well for us. Another thing that I should mention is the pipeline object. So one of the big differences between Vulkan and GL is this concept of a pipeline. In GL, you just have a bunch of state, you set the state, you add shaders, they're just part of the state, and then you do a draw call, and it gathers it all up and does the draw call. In Vulkan, there is this pipeline object which contains all of your shaders that you want to use at the same time, your full pipeline, as well as a pile of other state. It includes formats for your render targets, it includes your blending information, it includes all of your depth stencil operations and what you want those to do. It includes various information about multi-sampling. And the end result of all of this is, it also contains your full vertex buffer setup. The end result of this is that we do not have a single shader recompile in our Vulkan driver. The GL driver does a lot of recompile on demand. The Vulkan driver, when you go to create a pipeline, it fills out the shader key, compiles it, and there is your shader. It also emits about half of the required state setup into a 1K size block that's attached to the pipeline. And when you go to bind the pipeline, instead of recalculating and remitting all those packets, we memcopy. And the end result is that so we did some research on this when we were bringing up Dota 2. We were just kind of curious once we got everything up and running. So what does it look like having our driver under here? Let's run it under perf and see what happens. We ran it under perf, and initially it was pretty sizable. And then I realized I was running in a debug build with no validate, and we were recompiling shaders all the time, which just burned CPU like mad. Once we enabled the shader cache and built a release build, you basically couldn't see the driver. It was fantastic. So this sort of an overview of what we're doing from a draw call perspective. But there's also some other challenges that we had to deal with in order to make a competent Vulkan driver. So one of the challenges is memory allocation. So Vulkan does memory allocation a bit differently from GL. In GL, you create a texture, and memory magically happens. And if you call GL text image again, the memory can just silently go away and new memory come around if you wanted to. In Vulkan, things are not so flexible. It provides a much more explicit control of memory allocation. So you as the driver provide a set of heaps, and these heaps represent sort of the different memory types on your system. We are on a UMA, and so we have one heap. We have one heap on big core and 2 heaps on little core because we have concurrency issues. So you provide these heaps, and then from those heaps, the client allocates device memory objects. These device memory objects are potentially fairly large chunks of memory. And then out of those device memory objects, they sub-allocate for each of the different images. So they create either a VK image or a VK buffer object. They query that object for how big it is, and then they pick an offset into that memory object. And this does not map very well to the way that our libdrm interfaces work. Our libdrm interfaces are very much centered around You allocate a single BO for your single image, and that's just the way everything works. But it does map fairly well to the way GEM is set up. So a VK device memory object maps very, very nicely to a GEM buffer. Other objects have small bits of driver allocated memory. So you have an image view object that has a surface state associated with it that's a bit of indirect state that the driver needs access to. Your command buffer may have various bits of state. Your pipeline has various bits of state because we have, for instance, an indirect bit of state for blending information. So we have to allocate a little piece of state for that, and it's indirectly pointed to. So we had to figure out a way to manage all of these tiny little allocations. And one of the issues is that in our hardware we have these sort of base addresses, which different types of things are relative to different base addresses. So we have instruction state base address, which all of the shaders are relative to that one. We have surface state base address, which is for surface states and binding tables. We have dynamic state base address, which is for things like samplers, border colors, blending information. Depth stencil, I think, has something in there too, depending on your hardware generation. And so we kind of have to keep these different types of indirect state gathered together. And we really wanted to be able to, when you create a pipeline, for instance, go ahead and right there on the spot allocate and fill out your blending information packet. And when you create an image view, we allocate and fill out a surface state object. And in order to be able to do that and keep everything relative to the base address, we had to come up with a kind of a crazy memory allocation infrastructure that Christian and I are fairly proud of. So this is what it looks like. I've color-coded things by red is expensive, yellow is less expensive, green is concurrent lock-free, and blue is lock-free non-concurrent. So we have the basic device memory, which is just a GEM buffer. You call GEM create, gets you a buffer, that is your device memory object. Every single time you create a VK device memory object, you do an ioctl to the kernel. So there is some non-trivial cost there. We also have a BO pool, which we use for our batch buffers, and that is each BO is backed by an actual GEM buffer, but there's also a recycle pool in there so that once the driver gets into warmed up, we aren't making ioctls all the time. We're just reusing things out of the pool. For all of our tiny state objects, we have this block pool infrastructure that we set up. And it's kind of crazy. The core of it is this thing called a block pool. And a block pool is a single BO that starts in the middle and grows in both directions as needed. And out of it, you can allocate blocks that are all the same size. So when you create the block pool, you say up front, I want 4K blocks, I want 8K blocks, or whatever, and you can allocate blocks out of the block pool. And you can allocate from either end. So you can have, so when you allocate it, you get an offset, and it's either positive or negative, depending on which end you allocated it from. And the reason for the positive versus negative is because some silly restrictions in our hardware when it comes to binding tables having to live in the bottom 16 bits worth of your surface state base address. It makes it very annoying. In order to do this, it's backed by a memfd combined with user pointer. So we have this memfd, which we just get a memfd that's, I think, 2 gigabytes and call it good. And then we mmap out of the middle of it and use user pointer to turn that into a BO. And this has worked very well. And it gives us something that we can kind of control, but it's all backed by the same storage, and because the kernel is not making those pages real until we actually mmap it, well, until it actually pushes it off to the GPU, I think, we can go ahead and just create a 2 gigabyte user pointer, memfd, and use it all we want. Off the block pool, we have a state pool and a state stream. The state pool is a standard alloc and free type allocator where you give it a size, say a size and an alignment, say alloc, and it gives you a state object. You fill out the state object, you now have the state object, and you can reference it. This is what we use for all of the things we want to hang around for a while, like image views, which you create, and then they have some bit of surface state associated with them, and that thing hangs around until you eventually free it somewhere down the line because the client deleted the image view. The state stream is a little bit different. It's also backed by the block pool, but it uses a simple linear scan allocator and does not have a free function. So this is what we use for all of the bits of state that we need when we're building a command buffer. You just go through the command buffer. I need depth stencil state. Okay, go allocate me a depth stencil state. It gets attached to the command buffer. And then at the end, when we throw away the command buffer, we just reset the whole lot, and it gives all the blocks back to the block pool. And we do a bunch of stuff with the state stream. We use it for small states. We also use it if for some reason we need to suddenly generate a vertex buffer on the fly. We just pull it out of that. And that way it's all associated with the command buffer. When the command buffer goes, it all gets returned back to the block pool and freed up. So yeah, it's kind of a complicated infrastructure, but it has worked fairly well. And what it's allowed us to do is have things that are either allocated with the command buffer or allocated separately and kept around, and keep it relative to our different base addresses, which has been kind of painful. All right, so there's memory allocation. Another thing that gets interesting is compression and resolves. So most hardware today has some form of compressed surfaces. In our hardware, we have basically 3 different types of compression. We have high-Z, which is used for depth compression. We have compressed multisampling, and we have single sample color compression, which, depending on who you ask, that's 2 different types of compression. But so we have these different types of compression, and not all bits of the GPU can understand all of the different compression formats. So, for instance, on Skylake, most of the GPU can understand most of them, but prior to Skylake, the render engine understood everything, but then the sampler did not understand fast, clear compression. It did understand compressed multisampling. On Broadwell, it started understanding depth compression, but it didn't understand it on Haswell. So in order to deal with these different compression formats in both rendering and sampling, you have to do resolve operations at various steps in your pipeline. And one of the problems with an API like Vulkan, where everything is inherently multi-threaded, is you don't have a real good way to do CPU side tracking of when you need to do those resolve operations. So for instance, again, go back to the case where I have some texture that I'm sampling from in one command buffer and I'm rendering to another command buffer. Short of detecting things as the user submits them to the GPU and patching things up, there's no way that I can on the CPU track what the state of this image is and do the resolve at a later date. And so the Vulkan API provides a couple of different opportunities for you as the driver developer to do resolves. One opportunity is that it provides layout transitions. Our driver does not use these at all today, but they're there. And what it is that the user provides a layout identifier which tells you genuinely how the user wants to use the surface. So they can say, layout is render target optimal if they're going to use it mostly for rendering. Or they can do layout general, which is kind of this may be slow, but it'll work everywhere. Or they can do layout sampler optimal if they want to use it with a sampler. And then at various points, they will provide you these transitions where they say, the texture was in render target optimal, and now I want it in sample optimal. And you have to trust them that that's where it was and that that's where they want it, because if they give you the wrong information, you did the wrong transition. And at those points, you can do resolve operations or flushes or whatever else you need to do. It also provides this concept of a render pass. So this is something that's brand new in Vulkan. It does not exist in GL. And what it is it's a grouping of your draw calls. So you have some render pass, and the render pass has one or more subpasses. Within each subpass, you have a fixed set of render targets, and you're not allowed to change them. You're also not allowed to sample from any of them. And so you begin a render pass, you do a bunch of draw calls, you go on to the next subpass, you do a bunch more draw calls, you go on to the next subpass, etc. And you are not, like I said, you're not allowed to texture from something that you're using as a render target in your current render pass. There is a way that you can sort of fetch from the render target of one subpass in a subsequent subpass, but it's very, very constrained. And it's very explicitly designed so that if you're working on a tiled architecture, you can do the entire render pass per tile. You don't have to do a subpass for the entire image and then do another subpass for the entire image. You can do the entire render pass once per tile. And it keeps everything nice and constrained so you're not crossing the tile boundaries. But what this provides is it provides a nice sort of encapsulation of here's the drawing that I'm going to do from the application's perspective. So at the beginning of the render pass, you declare what you want, how you want the render targets to come in. So you provide a load operation, which can be load op don't care, or load op clear. Load means I want the previous contents to be in my render buffer because I'm going to do some blending or something. Load op clear is here's a clear color, please clear the entire thing. And then load op don't care is I don't care about those bits, I didn't want them anyway. You also have a store operation at the end of the render pass, which specifies, again, store or don't care. And this is, so for example, let's say you're using a depth buffer. So one of the common uses of a depth buffer is I'm going to bind a depth buffer, I'm going to do a bunch of rendering, I'm going to use the depth buffer to let my fragments be in the right depth order and get the right stuff on screen. But I don't care about the result of the depth buffer, I'm just going to throw it away. So in that case, you would say store op don't care because you don't care about what's in the depth buffer, you just wanted it to get you rendering correct. So you can also do the same thing with store ops. If you know you're going to cover every single pixel, you can just do load op don't care. Or you can do load op clear. And what this provides is it provides a nice sort of bracketing of the rendering. So at the beginning, if you do load op clear, we can do a fast clear operation, and then at the end, when you end your render pass, we can do all of our resolves. And the client is supposed to make sure that they cram absolutely as much rendering into a single render pass as possible. It is fairly clearly documented that render passes are very heavyweight objects, do not change them out at will. This is, again, very different from GL, where you just bind different frame buffers and go render stuff. And the driver is supposed to make that fast somehow, which means if you're running on a deferred renderer, you end up doing lots and lots of tracking to try and store the contents of your render buffer absolutely as late as possible because it's expensive. In Vulkan, the intention is that the client provides you that information and gives you a big fat render pass object. So that's sort of the framework you have for resolves. It makes it a little bit harder to deal with, but it does provide you most of the information that you need. And it's nice because it forces the client to actually think about these things instead of simply assuming it can make draw calls and they will go fast. So, is it easy to write a Vulkan driver? I would say yes, it is. Like I said, we did it in 8 months on 3 people and got a pretty complete conformant driver out of it. There's a lot of things you don't have to do. You don't have to do error checking. You don't have to deal with, there's no VK Vertex 4F. You don't have to have a VBO module and TLNL and all these other things. SPIRV is a little easier to handle than GLSL. I didn't really talk about SPIRV. SPIRV is the binary language that Vulkan uses. It's basically a binary encoding of GLSL. It's not all that interesting, actually. Another thing that's really nice is that, so we have Piglet, which is great. The Vulkan CTS is 115,000 tests that you don't have to write. One of the things that was very well done with Vulkan is we decided at the very beginning we're going to have a conformant suite, it's going to be open source, and we're all going to help make it good. And it still has massive test coverage holes, but it's getting much, much better as the days go on. And it is a lot of tests, and it has done a pretty good job. There's some things that are harder. You can't do CPU-side object state tracking. That's one of them. Another one, and this is something that we haven't really felt the pain of yet, but that is that apps have a lot more power for stupid. So you give the application complete control over synchronization, and they have the ability to get it wrong. And if they get it wrong and they file a bug against your driver, you have to go and hunt down why they're doing their stuff wrong and figure out what it is. Fortunately, the validation layers do a lot of tracking, but it's still kind of a pain. There's also not a lot of good tools yet. We don't really have a good API trace-like tool. There's a few things existing. The render doc is really awesome, except it doesn't work on Linux. There is a trace and replay tool written by LunaG that I've never been able to get to work. But the situation is getting a lot better as time goes on. So the last thing I wanted to mention was sort of how we did code sharing between Vulkan and GL. So there's a few different options here that you could do. And we considered all of them more or less. One is sort of the mega API approach, where you have one API and your driver implements its API, and then you have multiple other APIs on top of it. This is kind of the Gallium approach. It's also what we do in Mesa Main. There's a bunch of things you could try to do. You could try to do Vulkan and GL on top of Gallium. Unfortunately, Gallium to Vulkan is not a great match. You could try to do GL on top of Vulkan. That's also not a great match, thanks to the pipeline object. We could create a new API called Helium, because it's a lightweight API, and do both on top of that. But yeah, we didn't go that way. You could also just duplicate with impunity and just go for it and write two drivers. That's not a particularly maintainable solution. What we ended up going with is what I call the toolbox approach, where we built sort of some different pieces, and then our two drivers are built out of those pieces. So the sort of modern Intel open source driver looks like this. We have SOS-Intel Common, which has a few bits of common code, like the device info structures and some fairly non-interesting things. GenXML contains our XML files and our auto-generated fill-out code. ISIL is our brand new surface state layout library written by Chad. He did a fantastic job. It's really nice to work with. And it's far more correct and obvious than our previous code. We are currently in the process of trying to get the GL driver transitioned over to that. We have SOS-Intel Blurp, which is our blitting framework. Just to completely clarify things, no, uBlitter does not solve our problems. People keep asking me that question, and my answer is stencil. Our hardware is kind of crazy when it comes to stencil buffers and compressed textures, and you can't just use image views and call it a day. It doesn't work. So we have this Blurp library, which does blitz and resolves. We have Source Compiler No, which is our core compiler. Most of you have heard about that. And then we have what will be SOS-Intel compiler, although currently it still lives inside the DRI driver, which is our backend compiler. It has been completely separated out in that there is a nice single header file that provides 100% of the interface, and it's just no shaders in, binaries out. It's really nice. It's just still living inside the DRI driver because header file includes are going to be a pain when we move it. But we will get it moved eventually. And so what we've done in the process of building a Vulkan driver, not only do we have a Vulkan driver, but we also have a much better infrastructure for building a driver. Because we have all of these different bits. If somebody wanted to go write a new Gallium driver for Intel, they could do it. It wouldn't be that much work because you could just steal all this stuff. Not that I think that that's necessary, but it could be done. Because we've sort of taken all of the core API agnostic bits and pulled them out into these helpers that we can then reuse, and it has worked out really, really well. So that's my last slide. Do we have any questions?
There's a first one from the internet.
Okay.
Will the Vulkan driver see support for Sandy Bridge hardware?
No. We have joked around about bringing up Sandy Bridge. The problem is that Vulkan requires compute shaders, which Sandy Bridge does not support. Yeah. So we could implement a subset of Vulkan enough to run a few things, but it would not. But Vulkan just completely assumes compute shaders, which we can't do.
Okay.
So.
On the, I think the second or one of the later slides about building either another driver on top of Vulkan, the main issue, and correct me if I'm wrong, is this pipeline state object.
Yes.
Okay, so one the logical way to proceed would be the idea of a separable pipeline state object where the extension would run as follows. The application queries which portions of pipeline state have to be identical for the different object values that are passed in for pipeline state object. And then from that, it can build up its separable pipeline state object, and it has to follow the rule that if the driver is so insane, or if the hardware is so insane, well, you have to, the vertex and fragment shader are intimately tied forever. Or for example, everything, all the geometry processing is tied together, and fragment can be separate. I would think that'd be one way forward to build these things on top of Vulkan?
Yeah, so there's a couple of reasons. That's one of them. The biggest one is the pipeline state object, because for one thing, you're going to end up doing massive piles of caching of your pipeline state objects, because you end up creating duplicates.
Yeah, but
and
this-
we would have to create some sort of extension, like you mentioned, that allows you to make things more dynamic. Probably with some way that you could query what are the dynamic bits, and some way that you could set, here's my dynamic bits. Another reason is that there's a bunch of stuff that GL has that's sort of legacy things that are not in Vulkan. Nobody really wants to bring stippling into Vulkan.
But how do we do that now in I-965?
We have hardware for it.
Yeah, but the point is that would be yet another object you can pass to your pipeline.
Yeah, we could add it. We could add all of GL to the API or do shader workarounds or something. It can be done. It does expose enough hardware that you could do it. It's just not going to be pleasant.
But the line I'm advocating is the following: is that given a feature X, if the hardware has a simple way to expose X, like you set some bits for the rasterizer state, then you expose that extension. But if you have to emulate it through a shader, you never expose it.
Except there's things that are in Core GL that we're going to be emulating in shaders.
Yeah, I understand. I understand.
Kevin, this is a discussion, not a question.
Yeah. Any others?
So you mentioned that image layout transitions are essentially no ops in your driver. Is that correct?
Yes. In our driver, we don't actually do any transitions there.
Thank you.
You're implementing render buffer compression right now for the Vulkan Intel driver. Once you have full support for compressed render buffers, will you need to respect any layout transitions to do decompression?
I don't know. I think the answer is probably going to end up being no, and I've thought about how we could try to pack things in to do things a little more optimally with layout transitions. There's still some issues with formats that I don't think are incredibly obvious how we get at with layout transitions. I think we're going to have to keep it to render passes at the moment, but I haven't figured that out for sure.
Rex. Just a quick comment to your toolbox approach in the design. In the kernel community, we call that helper library, and it's a really established design pattern. There's a bunch of LWN articles.
Yeah. Well, and
people kind of want to.
Yeah, it's more or less the pattern we've used with No as well, and it's worked out very well there because we have different hardware that uses it, and they all call different passes, and it's worked out great there as well.
Regarding the toolbox, I just wanted to, not a question, I wanted to make a suggestion to anybody here who is contemplating writing a Vulkan driver. If you will to extract your memory surface management out into a toolbox library like we did, I decided to model our surface management toolbox library directly on the Vulkan image API. So it's a really tight correspondence. The ISIL surface management API really looks like the Vulkan image API with a few additional tweaks specific to Intel hardware. And the Vulkan image API is low level enough for this to work and for GL to use it. So all Mesa people, when you do this, don't invent a brand new API. Just copy the Vulkan API and do some setting and use that, and it works out really well.
Thanks. We are a bit late actually already. So thank you very much.
there were some connection issues. Oh yeah, phone.
Ah bon? Ça marche pas? Hmm. Compliqué, quoi.
Okay, guys, please grab a seat, and we're going to continue. Seems like everything should be set up. Okay. Just one thing, for the live stream, it would actually be nice if you could stand when you ask a question so people know basically who is talking. Very good. Okay, so I just need to start you. Here you go.
Hello?
Yeah.
Yeah, it's good. Yeah, we want to give a little status update, or we have a big status update about the Nouveau project, what we've done the last year. Think I will just start then. So we will talk about the kernel space, especially about the NYIF interface we built and power management. Then we will go to the user space and talk a little bit what we've done for OpenGL, for the performance counter, or for OpenCL and Vulkan. Then we will give an overview about the firmware situation we have with NVIDIA. We will talk a little bit about TechWare and Maxwell support, and how we see the cooperation with NVIDIA. So, yeah, last update was the last year, many improvements, okay. On the kernel side, we've got initial Pascal support merged for 4.8K, okay, for 4.8. We have mod setting enabled for all Pascal's GPUs, so they are basically useful for normal display stuff and things. We actually got acceleration firmwares for the GP100, which is a $10K GPU most users won't
So yeah,
use
why?
with Nouveau anyway, so why bother? But yeah, maybe we will get the others, other firmwares too. NYIF is a new kernel interface we wrote, or actually Ben wrote, for user space process to access kernel structures and functions from the Nouveau kernel module. It would also allow us to run Nouveau inside a virtual machine, and the support was already matched for free, and all user space libraries and processes are already using it. So on the power management side, I've worked on PCE link to change the PCE link, especially useful for prime setups, where you just offload on hybrid GPU laptops, and it gives a decent speed up for like everything. We have additionally improve the general clocking support for some Tesla's GPUs. We began some additional work for Fermi, and we also landed initial Maxwell clocking support in 4.9. We also have improved power consumption monitoring, and yeah, I will give more details about this tomorrow.
So hi everybody, I'm going to talk about OpenGL, what have been done since XDC 2015 and what we are planning to do in the future. So for Mesa 12 it was an exciting release. We added support for Maxwell 2 GPUs and as well as OpenGL 4.3 and OpenGL IS 3.1 for Fermi and Kepler. But it's not currently supported for Maxwell. I will explain in the next slide. And we did a bunch of different bug fixes and small compiler optimizations. So for the next Mesa release, I guess it should be Mesa 13. We added initial support for Pascal GPUs. And I added tessellation shaders for OpenGL, for Maxwell, sorry. And so now we currently expose OpenGL 4.1 for Maxwell and Pascal GPUs.
You can also say that there is a work in progress for image load store, and it's mostly done. It's just
yes. So all extensions for OpenGL 4.3 for Maxwell are currently implemented, but only compute shaders are exposed. So for the future work, the final goal is to have OpenGL 4.5. And so about OpenGL 4.3 for Maxwell. So the problem is how we schedule instruction for Maxwell, because it's really different from Kepler. So we have to write sched code data calculator, which can be used for scheduling instruction. So I started to work on that part. And
maybe you should explain what it means, the sched codes. Basically, every 4 instructions, you need to tell the hardware latencies on how much you need to wait for stuff, or if there are dependencies to other things. And so it's just, right now, it's just one number. We sort of understand it. Yeah. One number that is for each instruction, and we need to understand that way more. And I'm sure that in the process, we're going to get a lot of performance out of this, because because right now we may be very pessimistic and just say, hey, wait the entire time possible, just so we're sure that it's going to work. But then, yeah, it's not exactly the most efficient thing to do, because the GPU is just idle. So yeah, so by sched, it's not in the CPU. It really is scheduling instruction in the ISA.
Yeah. So I will try to implement this sched code data calculator in the next few weeks. And so we are planning to implement new features for Maxwell 2, like vertex and tessellation shader viewport, and post-dev coverage, geometry broadcasting, and conservative rasterization. I think AMD and Intel also have a similar extension for that, as well as a new rectangle primitive. And the last one is a configurable sample locations, which is going to be, I think, really easy to implement. So about bug fixes, a lot of different games don't work correctly with Nouveau driver. So for example, Formula 1 2015 just will hang your GPU. So it took me for some days to figure out where it hangs, but currently I don't understand why, so we try to fix the bug. And for performance, we also plan to do some compiler optimizations and some ZQL improvements. So we already have some pages for compiler optimization. So
Yeah, if anyone, well, maybe not in the room, but on the internet, is interested in helping in this writing compiler optimization, there are very, well, yeah, low-hanging fruits. There's a lot of them, and so if you are an interested student if you're interested in compilers, please come and have a chat with us, because, yeah, the compiler is sort of in a good shape. It's just that it lacks a lot of optimizations, and that could yield tremendous improvements.
So now I will give you a little status about performance counters, because I did two Google Summer of Code projects for that. So the current status, I implemented the performance counters engine inside the kernel, and now it's exposed by NVIF interface. All graphics performance counters for Fermi are already known, and so my plan is to rework the queries engine in NVC0 driver, because I think it will be better to use the batch of counters, and after that we can try to monitor performance counters and expose them to the H3D. So I have some branches for that, but I didn't work on performance content this year because I was working on OpenGL 4.3. I think it was more important. So
The Gallium HUD is basically heads-up display, of course, and it's something that Gallium can allow you as a user to put on, and you would see stuff like FPS or performance counters, CPU usage, memory usage, so it allows you to figure out what is going on. It's like Fraps, but much better.
okay, so next.
So then I'll be talking about OpenCL. So we did the first presentation about it at FOSDEM this year. So I won't go back over what we presented there, but I'll do a small update about what happened since then. So in a sense, there hasn't been much happening, but there has been some progress still. So the code has been updated to now support Fermi, Kepler and Maxwell as well. So it mainly means that what is currently working is also working on those cards as well. If you want to create those kernels, OpenCL kernels that you want to run, previously I was only using the CL-create program with sources, so that meant that the Clover will use Clang, a specific version of Clang, the SPV-LLVM repo that is being developed by some people at Kronos. And Clover will do the compilation itself. So that means that if I want to upstream my work, I would add to Mesa a dependency on something that is a version of Clang that is not upstream, which is not really ideal. So I added support as well for the create program with binary and create program with IL, which allows to upload directly the SPV binary of the OpenCL kernel's code. So that way the user has to do the compilation and Mesa doesn't get this dependency on a non-upstream version of Clang and LLVM. There has been some improved support for if statements, mainly because I added some really basic version of finode removal, because Nouveau Intermediate the Nouveau compiler accepts the input program to not be in a static single assignment form. So I need to remove all the finodes that can happen to be in the SPV code. So that also allows me to run some loops, except that I most likely run into a register allocation issue inside the Nouveau driver, which means that if you have more than two or more blocks inside your loop body and you use a variable in it that was defined previously, then the compiler will consider that it can just overwrite that value. It will use it once and then it can just reuse it for other things. So if that value is like the pointer to which you're going to write the data, then the pointer is going to be rewrote with junk data every loop run, which is not really great. So that will have to be fixed. Also, there's now some atomic operation support. So most of the ones, most of the SPIR-V opcodes are supported, except for the atomic exchange and swap and some atomic clear flags and set flags. But otherwise, atomic adds, atomic min and max should be working. And there was some bug fixing as well that happened in the meantime, like the different operations like divisions and so on were not using the proper signness before. So now that has been fixed. So what's currently going on? So I started adding textures and surfaces support. So it's still pretty much a work in progress and not working. On the way to XDCI, I thought that maybe I could try to hack an implementation of ARB-GL SPIR-V, which allows to use SPIR-V modules in OpenGL and try to run like the most basic GLSL shader using that. But I realized then that it doesn't look like the GL shader binary is implemented. And of course this extension uses that function to upload the SPIR-V binary. So it will wait some more. And of course there's a lot of code cleanup to do before any upstreaming. But I can do a quick demo of what's working. So I have this OpenCL kernel, which doesn't have a loop because of the reasons I explained earlier, where the register allocation will do. Not so good stuff. So I just unroll the loop manually, and it's going to sum all the elements in an array progressively. So if I run the code again, here we can see at the bottom that it's, oh yeah, we don't see the, I can increase a bit.
Input.
Yeah, the input is further down there on this line, so 5, 8, 2, 3, 6, 10 and so on. And if we go back 5, 13, 15, so it's adding all the previous elements and summing them up using some atomic adds. So I wrote it also the loop, if we go back in the other direction to make sure that I get a maximum of threads writing to the same position at the same time, just to make sure that the atomic add is working properly. So let's go back to the slides. So I'll do a quick talk about Vulkan, which is to say there's nothing there yet, and maybe next year we'll see what has happened in the meantime. But it will be, should be able to reuse this work from going to SPIR-V to the Nouveau intermediate representation, since Vulkan is using SPIR-V for all the shaders. So that's some work towards Vulkan support on Nouveau.
Okay, we're going to talk about the situation with firmwares now. So I assume that most of you know that there is something going on, but let's go through it point by point. So on Maxwell, the second generation of Maxwell, NVIDIA started requiring signed firmwares to do many things. So, for instance, the FEX firmware, which a group of firmware that is needed for the graphic engine, basically performs context switching, and the entire architecture that we have in Nouveau, and this is how it should be, is basically hardware context based. So each process gets a different context. And so if you cannot do context switching, then it means you cannot do any kind of desktop, which is, yeah, stupid. So until we have this basically firmware, we cannot do 2D, 3D, or video acceleration. So that's the first one. It's definitely the most important one. The second one is the PMU, which is the one doing power management, basically. Not entirely, but yeah. And until we have this firmware signed, we cannot access fan management. We cannot change the fan speed. So that means that basically, even if we could reclock from the CPU side and I mean the host side, since there's no fan management, we're gonna have, I mean, the GPU will have to overheat in order to get downclocked. Basically, it is really bad, and we could do something like in software to basically change the clock to regulate the temperature, but I don't think users are gonna love this. Like, oh, it's fast, slow, fast again, slow. No, let's not do this. So we really need this firmware. It also allows to do, well, efficient dynamic reclocking. That means that basically we can use this engine, the PMU, to poll on performance counters to know when we need to reclock. And it also does power gating, but this we don't support yet. He's going to talk about it tomorrow, Carl. Okay, Tegra support. So this is actually a very good thing. NVIDIA is contributing Tegra support. So it started in January 2014 for the Tegra K1. And it was basically a Kepler, the Kepler engine or 3D engine that was put on the Tegra family, but it really is copy-paste from the discrete GPUs. So that means that all the work that we did for this Kepler was, well, almost directly usable. One thing that was needed was first to say, okay, well, non-PCI Express /AGP platforms need to be supported because, yeah, we don't have any kind of hardware like this before. So that was the first patch that was needed, and then sort of worked. Then there was cache coherency issues because ARM is different from x86, but that was the extent of it. It was just a few lines, and the bring up was done. So yeah. What happened then? Yeah, in June, so a few months later, already got 2D and 3D rendering. It was a bit harder than expected. I mean, we could have expected it, but yeah, compared to other GPUs, is because the screen is not managed by the same driver on Tegra. There are two different pieces. There's the host 1X that does synchronization, some sort of command submission, and yeah, well, among others, anything related to display. And so that means that we basically expose two GPUs, one for the rendering, which is Nouveau, and the other one is host 1X, and so we needed communication between the two, and since also the user space is not really used to this, and this is something that Lucas was complaining yesterday about, then yeah, compositors don't really know how to deal with this, and there are patches for Western to make it work, but it's not very nice. Okay, in July, manual reclocking support. So yeah, and everything was merged in 2014. So all is well, but there was still some bugs with the context switching. So at some point, NVIDIA just released their own firmware for this, and it just works. And since no one really in the open source community cared about this, then we never fixed basically the open source implementation to work on this. It must be just a few lines of fixes, but yeah. So all in all, the Tegra K1 was just a breathe. It really was just changing code around and making sure that ARM would be taken care of. Basically any kind of what's the word for this? Assumption. The assumption that we had about we're running on x86 basically were taken care of. Then came the Tegra X1, which is Maxwell based, and you know what? It is GM2 something. That means that it requires signed firmware. And suddenly it was a bit harder. So the hardware got released in January. the basic kernel support landed in August. Okay, not too bad. Reclocking, power management is sort of there, sort of not there yet. So advanced features are also planned and worked on. But it's only in February, the year after, that the signed firmware had arrived to basically make it usable. Before this, you couldn't do anything. So yeah, not very nice. So even if NVIDIA is really committed to having upstream support for Tegra platforms, it still took a year to get it. Yeah, more than a year to get it upstream. Okay, so now we're going to talk about the discrete GPUs, which is probably what you are most interested in. So let's take the first Maxwell, which was basically a big change on the rendering side. So it did take us some time. The hardware got released in February 2014, but there was only one card that was announced and nothing else for the foreseeable future. On the kernel side, Ben Skeggs was really busy to basically re-architecture the Nouveau driver to be more flexible and modular. So it basically was a low priority, and support for it landed in 9 months later or 8 months later. I mean, the release, so basically it took 3 months before we did the bring up. Then out-of-the-box acceleration arrived much later in June 2015. Before this, you had to use NVIDIA firmwares, and it was sort of okay because we have scripts to get the firmwares out of NVIDIA, so it was fine. And since everything was plain in the binary driver, we could just be like, at this offset, there's the firmware, copy, paste, done. Put it in this file, and Nouveau is going to load it. So it wasn't really high priority for us to start adding support for Maxwell. The first Maxwell, because as I said, there was only one chipset and that was it. But then in September, more cards arrived, and oh shit, firmware is signed. We got warned about this about a year before, basically. Yeah, a year before at XDC in Portland. We got warned by Andy that this was going to happen. We didn't know when, and we started already discussing about what we could do. But, well, yeah, on our side there was not much we could do. So we're going to talk about this a bit later. So it did arrive, and basically we couldn't do much aside from mode setting until February 2016, so basically a year and a half later. Before this, we could not have any kind of acceleration. So wonderful. So yeah, very, very annoying for users. Power management is still stalled, so even though some firmware got released by NVIDIA, we cannot do any kind of power management on Maxwell 2. So that means, yeah, I mean, you know what it means. It was said before. As for Pascal, it was actually not too bad. It got released in July, and we got the patches almost immediately. So that was pretty good. So the initial support for the newer Pascals just arrived immediately. And we even got firmwares for the most expensive card, the JP100, which is basically a $10K card, as Carol said. And yeah, but if you have Nouveau and you have this card, then you may use it. Wonderful. But all the others, no. So that's very unfortunate. And this is what users really care about. So right now we cannot provide any acceleration for these cards. And we have no idea when this is going to land. Hopefully not in a year and a half, but yeah. So now the relationship with NVIDIA. So as I said, it started in 2013. At XDC, we got some documentation about some VBIOS tables. So that was really good, and we're like, oh, very hopeful. And indeed, it did spark a big change in the communication. So that was really nice. So what did we get out of this? So as I said, some documentation for VBIOS tables. Just a few. Unfortunately, it was the easiest ones. But still, it was nice. Then we got a register dump of the TK1. So that also helped. We did not agree on how to merge it to our own internal documentation, but since it's already living somewhere in a pull request, it's okay. We can deal with it. When we need something, we just basically look for in this documentation. So this way, it's not too difficult to merge something like, I don't know, 20,000 registers. Okay, NVIDIA did provide the code to implement Secure Boot on Nouveau. Not that we could have written it ourselves, given that we didn't have the firmwares. So yeah, there's more documentation than just VBIOS tables. So there were some workarounds for basically hardware bring up or enabling the graphic engine on boot, because it could have been power gated. But that's about it. The documentation is definitely not sufficient to write a driver for. Not that we would need this, but yeah, there is a limited amount of it. And we also got access to a mailing list. So mailing list on NVIDIA's side. On our side, it's just, well, yes, of course, a contact. But whenever we send email to this mailing list, we also CC the Nouveau mailing list, so everyone can see publicly what is going on. And this is fine. However, we've had problem keeping track with the requests, and so one of the NVIDIA engineer just is using GitHub to follow the issues, and yeah, so basically NVIDIA is also commenting there, and it's working sort of ish. It's a bit slow sometimes, but yeah. So on the Nouveau side, that's the problem. We are waiting for signed firmwares for years. And this is preventing us to do many things, and right now it is, well, fan management or power management on Maxwell 2, which got released, well, as I said, in 2014. This is 2016, and we're still waiting. Yeah, there's no acceleration on Pascal for all intents and purposes, unless you're very rich. We are waiting for the BIOS documentation, because starting from Maxwell 2, the BIOS is now signed. That means that we have a tool to upload a fake BIOS, so basically we edit the BIOS, then we recompute the checksum and all this, and we upload it in memory in the shadow ROM, and then usually the proprietary driver would see, oh, it's there, so I'm going to just load it from memory and not read it from I2C EPROM chip. So this is really good, but since now it is signed, we can't change anything. That means that how can you reverse engineer a big blob of bits when you cannot change the bits to check what is going on? So luckily we can do some reverse engineering on all the platforms, but as time goes on, I mean, Maxwell did add a lot of things and we cannot reverse engineer it. So without documentation, we are stuck. And so that means that we are basically losing interest in new platforms, which is not a good thing, because this is beneficial for everyone if we could work together. So NVIDIA, please allow us to help you. Free labor. So what would we need? Let's say in a perfect world, but then some would say a sensible world, we would get early access to hardware and firmware, and we're not talking about years, we're talking about just before the release. Well, if you have engineering samples or something like this that you do ship to customers, so nothing that would be for engineers, so that would have more access to the hardware than we need, then yeah, we would need this basically for the hardware and the firmware at the same time, otherwise we're stuck. So it's good to have mode setting, but it's not exactly all that we need. And NDAs would be fine for this. It's not like we would be hostile to it, as long as they expire the day the hardware ships. We don't want to be in the situation where basically we have the code, we have the hardware, but we can't release it because lawyers. Yeah. So it makes no sense if, I mean, the point here is just to get early support so we can provide some sort of support, at least mode setting and things like this for early users to make sure that, you know, it works on Fedora and things like this. And we also need the documentation for the firmware's ABI. Otherwise, that means that we need to do decompilation or stuff like this, and this is, you know, in the law, it's okay if we just have a look at what the proprietary driver is doing. It's another thing to change or to have a look and decompile stuff. So we need this ABI. We also need the rights to redistribute the firmwares. Right now we are in this situation where we ask users to extract firmwares on their machine. So we do have a script for this. Luckily, sometimes you don't need to run anything. You just take basically the installer provided by NVIDIA, and then it just extracts it and gets finds some headers, zlib headers from the version, and kind of guess the offset of stuff and boop, extract it. So that works for the video firmwares, but that doesn't work for everything. Especially now that everything is signed, we really struggled to get access to the firmwares. So the VBIOS documentation, as I said, since we cannot, we cannot really do the reverse engineering, we would need this BIOS documentation, and actually we also need access to, we also need to be able to upload firmwares, VBIOS to the card and let the blob work on it, because otherwise, how can we verify the documentation? I mean, who has ever saw a documentation that was actually accurate, right? So we need this, and this could just, you know, be a module option, and this is not something that should be not doable, especially since we only need to get rid of the signature check on the shadow ROM. So no user would use this anyway. And yeah, because every time you reboot, basically you need to re-upload the BIOS. Okay, and the best would be for NVIDIA to adapt their firmware policy and actually release the firmwares independently from the proprietary driver. But you know what? This is what we've been saying since 2013. Let's be honest, I don't think it's going to happen. So how about this? We just get something and we deal with it. As long as we got ABI, we may just be able to just wrap around it, make one nice interface and be done with it, and not just trying to be perfect. And yeah, so as long as we can have versions number inside the firmware, all is well, or in the file name. So if all this were to fail, basically the Nouveau community is going to shrink, because if the driver cannot be used by users, then, you know, we're not going to get developers. Developers are going to lose interest because they cannot use their own code and have fun. So yeah, it's gonna. This is what's going to happen, and also NVIDIA will have to write support for newer chip, and not only for you know, the small changes necessary for Tegra like they did for the TK1, but they actually have to do the full bring up. And then, as Nouveau developers, how do we test it? If we do not have the firmwares for the discrete GPUs, then okay, we may get some samples from NVIDIA for the Tegra, but I mean, we don't really use Tegra as it's just yeah, embedded stuff. So then they would have to convince us that they're actually gonna maintain the code, otherwise it shouldn't get in to begin with. So we are in a situation where actually it would be very, very beneficial to NVIDIA to understand that, yeah, you cannot just expect code to just land in upstream and be done with it. There is maintenance, and we need, yeah, right now Nouveau is the only driver that supports NVIDIA card, and there's not going to be any a second one. This is not going to land in the kernel. So, yeah. So hopefully this is something that management at NVIDIA will understand. There is a risk of not collaborating. And finally, who are we? Because we could have said it before, but hey. So the free engineering team is Ben Skeggs from Red Hat. So he's the main kernel developer and the maintainer of the Nouveau DRM. So he is the one doing all the bring up, and sometimes he does get access to some samples, so it's good. Then Ilya Merkin and Samuel Pitwaze have been the main Mesa developers. So this, they've been doing tremendous work, and they are building on the work from Christoph Böhmiller, who's or used to be a physics student and just wanted to play StarCraft. So that's how basically the project really started for the user space. And before this, it was Stéphane Marchesin, actually. And for the other contributors in alphabetic order, so Alexandre Courbeau from NVIDIA, so doing the TK1 Plus development and maintenance. He's been doing a lot of work, and he really has, he means well, and he really is trying to be helpful, but there's only so much he can do. Then Hans de Goede and Pierre Moreau, who are working on OpenCL support. Carol Herbst and Roy Split, working also on power management and performance, just like I do actually. Should have been just there. And Emil Velikov have been working on the basically random fixes and robustness of the Mesa code. So thanks to him, he's also the Mesa maintainer. And yeah, you were also interested in having new people coming, and even though the situation with newer generation is a bit grim, luckily we still have a lot of tasks for all the GPUs, and until the situation is resolved. But of course, it's not sustainable. But if you do have old hardware like Kepler, which is not that old, but it's dating now, you can still benefit from helping us, and you would get more performance if you would like to work on compiler. Or you could get more stability in the source code by having, basically helping on the quality assurance. So testing it yourself is already good from Git, of course. And but we are also building a CI infrastructure. So if you're interested, please come and help. Okay. Okay, some links, but this is mostly for people in the stream. So, any questions? We'll need the second mic. Oh.
I don't really have anything specific to say, but I feel like I ought to respond. So I guess first of all, from NVIDIA, I want to thank the Nouveau community for all the work that you guys do, and I guess I personally want to apologize for how poorly NVIDIA has engaged in the past 2 years. I think clearly articulating things as you have on the slides and the video stream will help my escalations within the company. I probably shouldn't say any more about that for now, but thank you for clearly articulating the problems, and here's XYZ things we need from NVIDIA. I think that helps and is easily translatable when I go back to managers. So thanks for that, and I hope that we can improve the situation in the near future.
Yeah, let's work together. This is definitely...
Yes.
No one is hostile here. It's, yeah.
Okay, so again, thank you, and my apologies.
Thanks. Can you pass the mic? Yeah.
Hello.
Okay.
My question is not about the actual topic of the talk. It's more about your day-to-day hacking with the project. So when you're actually doing some driver development on Nouveau, what kind of setup do you have? Is it like you're running your desktop on the integrated GPU and then inserting and removing the kernel module, booting Mesa? Do you have another PC for testing the code, and you develop on a laptop or something? Just tell us about your setup.
I guess it really depends on the people, but since I have probably the setup that is the most used by developers here, I can explain. So I do have a separate machine called, Ariata, so reverse engineering ATA. So that's my machine that I use where I just plug cards, and I have my separate desktop where I just push code and do compilation and yeah. So because we do hang the machine all the bloody time. And I once moved away from basically my apartment for a few months to Canada, so I needed a system to be able to reboot the machine. So I made a system like IPMI, but it's much cheaper, something like €100. And so this is something that now many Nouveau developers have been using. So whenever they need access to hardware, they just ask me. I have something like 40 NVIDIA GPUs, and they tell me what to plug. We can plug right now 2 GPUs, And so yeah, basically they get access to it. So Samuel has been using it quite a lot, actually so much that sometimes I have problem to access it. Yeah, and then Carol, you use your laptop, but maybe you can talk about it if you want. Oh, you're silent. There you go. Okay, now it works.
No, it works. Okay. No, I'm just using my laptop. It has 2 GPUs, so Intel one and then NVIDIA one. I usually use DII3 offloading with Prime, and that allows me to also unload the NVIDIA Nouveau driver while X is running, and I can also easily switch between the 2 drivers and just do some hacking on this. Yeah, that's mainly what I use.
Yeah, I guess someday we should document the kind of process we have. The most insane reverse engineer that we have, Marcin, has, I should have put a photo of it actually. I went to his flat a few weeks ago, and he basically has an entire shelf, and then he screwed motherboards on both sides of the shelves. And he has something like 15 different PCs, and then he also has a system to turn on and off machines remotely, like I have. So yeah, we do have a lot of hardware that is necessary for this kind of work, especially now that we're working on improving CI. We need multiple machines, and we need to be able to reboot them, and blah blah blah. Yeah.
So what kind of documentation produced by the Nouveau project would a new contributor need to read, and where do you keep such documentation?
Do you want to answer? Okay, I can do
on
it.
That. So I can just show an example here.
So there is the XML-based documentation.
So if I ask, for example, from the G96 chipset, I don't know, like the 0 register, for example, then it will print what the different fields are, and if you put some value in it, then it will tell you what the value contains.
Very small font.
Oh, yeah.
No.
So,
Like that.
yeah, this is one thing, but this is just for one access. But then we have MMIO traces. We basically dump everything that goes through the PCI Express ports to the card, and we get millions of these lines. And we just, scroll through them, and whenever you see something that is not, for instance, in red here, it tells you, I don't know what these bits are. And whenever there's new hardware,
like
you'd be like, okay, well, I need to figure out what these bits are. So you just go there and you bash them, and you try to make them change by sometimes bashing other registers, and this is how it goes. Oh yeah, my MMIO trace.
Yep.
Very good.
That's the stuff NVIDIA does with the hardware, basically.
So this is the main way we actually keep track of how to do the posting, basically bringing up the card at boot time, and then we have a separate tool that is sort of similar for graphics, but it's as it's commands sent to a batch buffer, we need to have a different tool. It's easier this way. Okay, well, I guess, okay, I think we're a bit late, so very quickly then. It's not on.
On a much earlier slide, there was mention about the GL SPIR-V extension.
Yes.
Do you have anything more concrete about what the plan is for that? Are you guys going to do the common code, or are you waiting for someone else to do the common code, or?
Well, I was not thinking in the beginning of doing that. It's just like before the XDC, I thought, okay, maybe it could be interesting to see how it works, because I've been mostly focusing on the OpenCL part. So all the GLSL primitives or built-ins are not supported at all, and the matrices are not. They could be working, but it's not. It has to be tested and further improved. So it was more like just to test. So I just try to expose the extensions from Nouveau point of view, and then realized that the shader binaries was not there, so I didn't go any further. But I probably continue working on textures and surfaces first, and then once that's done, maybe I have another look if no one has taken a look at it and try to do something.
You're going directly from SpearV to your backend IR.
Right.
Okay.
Like.
Okay. Next presenter, please. So please check out what Roy said up there. So Marcin has been, as he says, invaluable.
Martin, were you good to go? Or? Okay, good day. My name is Peter Hatra. I work for Red Hat on the input stack, mostly libinput. And despite the previous announcement on the program, I'm actually going to give you an update on pretty much the whole input stack from the kernel up to GTK, rather than just focusing on libinput. So the way I've split it up... Hello? All right, I'll continue as soon as my computer starts responding again. Any minute now. For fuck's sake. All right, let's try again. Okay, so again, I'm Peter Hatra, work for Red Hat. I'm going to give you an update about the input stack. Sorry about that. My computer has a tendency to crash when I plug an external monitor in. So the way I've split it up for today is I'm going to talk a bit about touchpads first and what we did over the last year, about tablets, about mice, about keyboards, and then a little bit of the infrastructure stuff we've done in the last couple of months to the X server itself and the Xorg infrastructure in general. So let's talk about touchpads first. In terms of the kernel, for a lot of the touchpads, the Synaptics ones, we're still using the PS2 protocol in the kernel. One of the biggest problems with that is that we only get 2 touches from it, even though the device itself would, in theory, be capable of doing 5 touches. We have very limited bandwidth, so the quality of the position data, as soon as we have more than 1 finger down, is pretty shoddy. And the firmware testing is getting less and less, so we actually had a couple of bugs where the firmware for PS2 just wasn't tested when they released the product, and then we had to work around all these issues in either in the kernel or in user space. In one case it was even worse because the firmware then got fixed on the next generation, but we didn't know that the firmware was updated and so on and so forth. So right now the focus is to try to get away from PS2 where possible. The new hotness in terms of Synaptics touchpads is RMI4, which has been around since, and I think default in Windows since about 2010, so we're only about 6 years behind. It gives us multiple fingers, usually 5, which is a pretty good average number of fingers. It gives us more accurate axis ranges and resolutions. One of the problems with the PS2 protocol is that it still has to be backwards compatible to the axis ranges that they defined back in the day 10, 15 years ago. So the axis ranges in Synaptics touchpads are actually always the same, and just the resolution changes. In terms of where are we with RMI4? We have the RMI4 core is upstream now. We are using it for the I2C and SPI transport layers. RMI4 over HID is currently in process. I think it's waiting for a reviewer comment. I don't know, have you gotten anything back from that yet? Okay, so kind of working, still in progress. RMI4 over SM bus is in process for kernel 4.10, or at least that's what we hope. We already have for Dell and a couple of other touchpads, one second, we already use HID over I2C. So in case you're seeing like weird touchpad names show up, that's the case where we already do that. If you have a Synaptics touchpad, you will need the new hotness because it significantly improves it. If you have any Lenovo's, I think they're all, or almost all of them, are Synaptics touchpads. So side effect of the change, so when we switch away from PS2 to I2C or to RMI4 means that the device names change. So right now, almost all of you will have a device called Synaptics in PS2 touchpad. The device name will change to something like this. So the first one is the RMI4 touchpad name. If you have a Dell with I2C, you're going to see a touchpad name like this. One of the problems we're going to face in that in user space is that anything that currently matches on the touchpad name, which is almost every xorg.conf snippet ever created, is going to be invalidated by that. Not the worst of all things because we want to move people to libinput anyway, but that's just something to keep in mind. Benefit we get from that though is better responsiveness from the touchpad. The other side effect is we get a mute touchpad device. We still get the PS2 touchpad device, but it's not going to send any events. We looked into trying to remove that so that the kernel doesn't actually initialize it, but the dependence is on making sure this doesn't happen. It's just too complicated, so we just decided it's a cosmetic thing. Anyone in RMI4 is just going to have like a TM353 or 4 touchpad. That's the one that actually sends the events, and then one other one that just looks like a touchpad but doesn't do anything. Going one layer up the stack to UDEF, we've introduced 2 new properties in UDEF, so we now tag trackballs as well. So in user space you can rely on a trackball actually being tagged properly and you can detect them. I think GNOME has already started doing that for I think point acceleration configuration or something. And we also now tag touchpads in terms of whether a touchpad is an internal one or an external one. Again, for GNOME and for libinput, that's quite handy because what libinput, for example, does is if a touchpad is an external one, we don't enable disable while typing because if your touchpad is somewhere sitting next to the keyboard, you're not going to accidentally touch it while typing. So we only do that on internal touchpads. We have a whole bunch of axis range corrections. I think it's somewhere like 45-ish or something right now for various model numbers. Usually what happens is that the resolution doesn't quite match the real world. So the touchpad says it's like 5 centimeters wide when in fact it's 10 centimeters wide and so on and so forth. This affects a lot of things, including point acceleration. libinput does in fact use the physical distances for almost everything. So if your resolution is wrong, your touchpad is not going to behave the right way. RMI4 is a bit of a problem there because of the changed device name that will invalidate some of these hardware database entries that we have at the moment. But we're also hoping that because RMI4 is a better protocol and more accurate, that we might not actually need all these corrections anyway. So we'll see that as we come along. It's just a whack-a-mole, so as soon as one touchpad is broken, we have to fix it, we wait for the next one, and so on and so forth. There's not much else we can do there. Moving one layer up, in terms of touchpads for libinput, our goal is for libinput to be better than XF86 input Synaptics, which is like the obvious plan. That's not universally true yet. Point acceleration is a big ticket item. A lot of people saying that the libinput touchpad point acceleration isn't quite what they want from Synaptics. I did try to figure out what Synaptics actually does. So if you want a bit of a laugh, read that poster link there. Synaptics point acceleration is essentially a random number generator. One of the things that also hurts us, especially for touchpads and libinput, is that we don't use SIG.io in the server. I'm going to get to that later when I talk about the Xserver infrastructure. But it just means the touchpads aren't quite as responsive yet as they used to be with Synaptics. But come server 119, that problem should be gone. Little anecdote on the side, one of the things we tried to remove, because we now have modern touchpads, we tried to remove the touchpad hysteresis, which essentially means if you hold your finger still on all the touchpads, you still get a lot of wobbly effects. libinput works around that by essentially requiring you to move a minimum distance before it starts moving the pointer. So on newer touchpads like the T440 I have here, newer generations and stuff, we figured, you can put your finger down and the firmware will filter that out for you, so we don't need that. So we removed that from libinput, and then we played whack-a-mole for about, 2 releases, because suddenly almost everyone had a wobbly cursor. So eventually we brought that back by default, so that was just one of the things. We tried something, didn't work, so we went back. One of the things we also found is like libinput gets a lot of cursor jumps. When you switch to two-finger scrolling, from two-finger scrolling to gestures and so on and so forth. Synaptics didn't get those, and we couldn't quite figure out for a while why this was happening. So it turns out that a lot of the touchpads would actually give us, just don't track the fingers correctly. So there was a couple of cases where you put 2 fingers down, and the kernel tracks it in 2 separate event streams called slots. And then as you release one finger, the kernel would actually terminate the other finger, and then continue on the finger you released with the coordinates of the other touch point. We now fixed all these things, but the interesting thing is Synaptics is still single touch. Synaptics doesn't do multi-touch. And that didn't see these issues because the single touch emulation in the kernel actually didn't see these problems. So it's just one of these cases where stupid wins because trying to be fancy actually hurt us in that particular case. We have a bunch of hardware quirks. For example, for the Lenovo 60 series, the trackpoint sends random events. Even though when you're not using it, you're either using the touchpad or you're typing, and every once in a while, somewhere like every 3 seconds, every 20 seconds, who knows, you get one trackpoint event. libinput would use that to enable the palm detection on the touch point, on the touchpad, and suddenly your touchpad would stop responding for 300 milliseconds. So we fixed that recently. On the 50 and 60 series on Lenovo, if you move your cursor slowly enough, the firmware will just randomly filter out the movement. So you can see your cursor move, then it just stops, and then it keeps moving again, even as you move your finger continuously. We found out that's just a firmware issue. We can't really work around that. So we probably need like a special, what we're planning to do at the moment is that we change the pointer acceleration for that specific model. So it moves, the pointer moves slower by default, so you have to move your finger faster to get the same pointer movement, because as soon as you move your finger faster, you don't trigger that firmware bug. Yes, pretty much. There's not much else we can do. We can't obviously fix the firmware directly. One other case is the HP 850-8510. It's a multi-touch pad that doesn't actually do multi-touch. So we have a hardware quirk in that, and so on and so forth. So we just keep accumulating things like that. We've fine-tuned the scrolling and the gestures. We've disabled gestures on a whole bunch of incapable touchpads, like the semi-MT ones. You can't do pinch gestures on those anymore because the data is just garbage. We're still struggling with the 2-finger scroll with this gesture decision. It turns out that by the time you know whether something is a pinch gesture or whether it's a 2-finger scroll is well past the time of when you already we're supposed to have started sending events for it. So we're still trying to fine-tune these. We're currently heavily biasing to two-finger scrolling because 90% of two-finger movements are going to be a two-finger scroll. So just like, fine-tuning there and there. Next item is tablets. Tablets, not iPad-like tablets, but the digitizers, so the Wacom-like tablets that the studios and designers tend to use for drawing. In terms of the kernel, it's still, Wacom devices are still very well supported. Wacom has 3 Linux kernel engineers working on device support. Other tablets are a bit more random. So there was a project by Nikolai, who is over there, called Digimend. Unfortunately, where it was enabling these tablets one by one, pretty much. As users bought hardware, he tried to buy hardware and tried to enable them one by one. Unfortunately, they're shutting down now just because of lack of time. So in terms of the kernel support, Wacom devices tend to be really good supported. The rest depends very much on the tablet. Wacom KO, so the kernel module, had a massive cleanup in the kernel. The biggest change visible to user space is the LEDs on the tablet, and are controlled by the kernel as well through the proper LED subsystem. So if you have an Intuos 4 or 5 or any of the newer generation, as you press the center button, the LEDs will actually keep cycling, which is something we now use in libinput and in GNOME as well. One of the bigger issues is that Wacom.ko used to require manual device support, so whenever there was a new generation coming out, we needed to have the engineers add the new device and so on and so forth. So one of the things we changed, I think Benjamin was mostly working on that, we switched to HID descriptors, which made the integrated screens work out of the box without any kernel updates. And we also have plans that the future devices will make use of the same HID descriptors. So in the future, hopefully, if you buy a new generation Wacom tile, you can just plug it in and it'll just work instead of having to update the kernel or waiting for a kernel update. So no more engineering input needed until we come up with new features where we suddenly need the engineers to kick in again. In terms of libinput, tablet support is complete. It's split up in a couple of sections. So we have tool support, which is for the actual pen. We have pad support, which are the buttons and the touch rings and touch strips on the actual tablet device. We have pad mode support, so we can do things like you can map the buttons depending on what LED is currently illuminated. You can say, okay, so in mode 0, which is that LED, button 1 maps to forward. In mode 2, button 1 maps to, I don't know, close application or something. And we have touch support, but we've had that for a while because in the end, it's like Wacom tablets are just either the giant touch pads or they're just giant touch screens. So we've had that for a while. There wasn't anything special there. For tablet tools, the big change to what we had in X, we just had to pretty much initialize everything on a static basis. In libinput, we can do that on demand. So as soon as you bring a pen into proximity, we get a new tablet tool with that serial number. We can track that pen across multiple devices. So especially the studios tend to have multiple tablets attached. So with the pens that have serial numbers, you can literally say, if the application supports it, you can say, I want this pen to be blue. And then if you use it on that tablet and then move across to the other tablet, the application can follow that. So you can use the same physical pen across tablets. We have per tool capabilities. So rather than X, where we just say every tool has every capability, and then we just don't update some axis, in libinput you actually know, okay, this pen will have tilt. We have physical access where possible, so distance and pressure are arbitrary, but we actually get the millimeter position and so on and so forth. And we have absolute and relative movements as well. In terms of tablet pads, there are their own event nodes in the kernel. They have 3 event generating items, so buttons, which are easy, rings and strips are just little touch devices on those things. We have a very custom tailored API for those pads. The reason why it's custom tailored is because there's very specific use cases on how tablets are being used. And we tried to put it into a more generic API, but it turns out that even though like a TV remote is also a device that just has buttons, it's used very, very differently to the way how a tablet pad is used. So we decided to make this a very specific API. So the modes I mentioned before, so usually we have a couple of LEDs on the device, which are sort of illustrated here with reddish. The control moved to the kernel's LED interface. So what happens now is like regardless of what user space you're running, the kernel will cycle through the LEDs, and then we can hook on to whatever we actually want. So we're currently working on, in GNOME at least, we're currently working to get this into OSD, so on-screen display. So as you press the button, the LED cycles, but you also get like a nice display, say like you're now in mode 2. So you know that the ring now works as a scroll wheel, versus in mode 1 it used to work as like zoom in, zoom out, or whatever you assign to it. In terms of Wayland, we have a tablet protocol up to V2 now, which is split up into Tablet Manager, which is mostly like a protocol requirement. We have per seat, which everything in Wayland is per seat anyway. But you can see it pretty much copies what I already talked about. We're going to have a tool, we have a pad, and inside the pad we have a ring and a strip. And then we have the normal button events, we have the axis events, and so on and so forth. So the tablet protocol is fairly straightforward. It's large just because we get a lot of data from the tablets, but it's fairly straightforward in terms of understanding. And as of 3.22, GTK Plus tablet support is feature complete for Wayland. So that already works. The only thing that's missing from the GNOME is we're still lacking some of the configuration bits. So the control center, for example, can't configure it just yet. Most of that is almost ready, but it's just not quite merged yet. So yeah, so we have almost full stack. Like if you look at GNOME, we almost have full stack support for tablets now. In terms of mice, one of the more interesting things is we're moving for Logitech mice, so all the ones that use the unifying receiver. We are currently moving the battery starters into the kernel. So this is going to be exposed through the normal kernel power interface. The first time we got this working was quite nice because as soon as I plugged the receiver in, GNOME already popped up something, oh, this mouse number 2 is low battery. So that's the user space stack for that is already there. We just have to put the kernel stuff in place, which means it gives us a standardized interface for GUIs. So I expect KDE and XFC and stuff may have something similar. But the main thing is like the core interface is standardized, so we can hook onto that now. That's in progress, that's not merged yet. Slight anecdote we found with libinput. This particular mouse, the Logitech MX Master, kind of threw us out because libinput provides the physical angle for mouse wheel as part of the event data. So you both get, okay, this was 1 click, but libinput will also tell you this was a click by 15 degrees or 20 degrees depending on the mouse. Turns out that on this particular mouse, the click angle for the mouse wheel is different for the horizontal mouse wheel as for the vertical mouse wheel. I'm not sure who decided on that, especially because the horizontal mouse wheel doesn't actually physically click. It sends click events, but it doesn't actually have a click thing. So you just rotate it continuously, and whoop, suddenly you get an event. So again, like just these weird hardware quirks we have to put in just because hardware is out there. In terms of Wayland, we've added a relative pointer protocol, and by we I mean mostly Jonas Odal. I hope I pronounced his name correctly or roughly correctly. Relative pointer Wayland protocol is basically that's what we need to use for what people want to use in games eventually. If you want to have a 3D shooting game or something, you need the relative data from the mouse. It provides accelerated and unaccelerated motion data, so you can either use the desktop acceleration properties or you can just do your own acceleration in your shooter game or something like that. We also have a protocol for pointer confinement and locked pointer. So use cases are, for example, if you have a virtual machine manager or something, you want to lock the pointer within that window. That is something that's not supported in the core protocol, core Wayland protocol. So we have like this extra protocol. Both of these are still unstable. The tablet protocol I mentioned before are still unstable as well, so we're just waiting for a bit more implementation here. We also have on the list, we have an X-Wayland proposal to emulate warp pointer handling, because in Wayland itself you can't actually warp the pointer, because A, you don't know where you are on the screen and you're not supposed to control the pointer anyway, but there's X applications that need to do that. So Jonas came up with a patch set that as soon as you have an X-Wayland application that warps the pointer, will actually lock the pointer in the surface of that application and then switch to relative events and then essentially have a ghost pointer using the relative events that you can send down to the application. And then as soon as you leave the window, you just undo the whole thing. It's a bit quirky, but it seems to work. LibRatBag is a project we started talking about last year. It's like a generic library to configure gaming mice. That has taken a bit of a backseat over the last year. The current device support is listed here. We do, as far as I remember, we do support profiles on all of them, so you can change the resolution, you can change how many profiles you want, how the buttons are being mapped, and so on and so forth. The G.Skill MX780 LUD enabled yesterday, for example, so that's, I don't think it's merged yet, but at least we have profiles working on that now. Follow-up from last year as well, Keith, the most expensive mouse we've worked with now is $159 US. So we're keeping track on what the most expensive mouse is we're working with at the moment. We have RATBACK-D now, which is something we talked about last year, which is a dbus daemon that uses libRATBACK to talk to the mouse so that you can have a normal application configuring the mouse. David Herman started on that. That's working now, systemd enabled, and so on and so forth. We have a GUI application called Piper, which looks roughly like this. It's a standalone application. We decided not to make it part of like the GNOME Control Center or something because A, it's a very niche market to begin with, and B, it's only something you only configure once in a while anyway. And we don't actually store anything on the machine, so anything we change on the device, we store on the device directly. So Piper looks roughly like this, which also gives you an indication that no designer has actually touched this yet. A side effect of libRATBACK was a library called liblur to access Logitech unifying receivers. The eventual goal for that is that we eventually replace the various home-cooked solutions everywhere. I don't know how many implementations of the Logitech HIT++ protocol are out there, but there's at least 5, 6, 10, who knows. So ideally we have like this little helper library that we all have all this in one place. The side effect of that was what I mentioned earlier already, we're going to move the battery starters into the kernel. But things like, for example, if you have a Logitech unifying receiver device, if you want to pair that with your receiver or something like that, hopefully you're only going to need one library instead of every project having its own library for that. Keyboards. We've done exactly nothing because nothing needs doing. They still send keys event on, and then the rest is XKB. In terms of Xorg infrastructure, there's 2 items we did. Or 1 item we did and 1 item we're about to do. We've added an input thread to the X server, and we're about to retire the legacy input drivers. So in terms of the input thread, up to server 1.18, up to including server 1.18, we had a SIG.io-based approach. So all the input devices register a file descriptor to the event node with the signal handler. When you get an event in from the device, it triggers a SIG.io, and all the event handling is actually done within the signal handler. So that includes point acceleration, screen mapping, hands-on, pointer mapping, and so on and so forth. But more importantly, cursor updates happening in the SIG.io handler as well. This makes it feel responsive because it doesn't matter what the X server is currently doing. Your mouse cursor will always move when you move the mouse. If you look at the man page, Signal 7, you get a bit of a hint of why this is a bad thing, because you can't use malloc, you can't use printf, you can't use anything that's particularly useful. There's a list of functions you can use within the signal handler, aside from the whole like shoving half of the knowledge into the signal handler is a general bad idea anyway. So Keith, oh no, wait a minute. Okay, yeah, so libinput can't use the SIG.io approach for a couple of reasons. A, we want to be using things like malloc and printf in libinput at any time when we need it. And B, certain things like tablet support. If you come into proximity, we need a new tablet tool. We can't pre-allocate all that. So one of the side effects of libinput not being able to use the SIG.io approach is that when the server is busy, input stalls. So you might have noticed that, especially in Firefox, if you start scrolling, suddenly everything just starts lagging because Firefox just keeps rendering, and the input events don't get processed as fast as they should be. So we now have an input thread, thanks to Keith. The server starts a separate thread to pull all input FDs, so it's pretty much exactly the same as before with the SIG.io handler, except that instead of doing everything in the signal handler, we now have a separate thread for it. So the events are picked up, the events on any input device. We only have 1 thread for all the devices, so the events are just picked up by the thread, continuously processed, and all the point acceleration, screen mapping, cursor updates, what we did before in the signal handler is now handled in that second thread, which makes it feel much more responsive than before. Of course, one of the problems is that as soon as you start adding threads to your program, you're going to have a lot of race conditions. We've fixed most of them now. I think there's 1 left where it crashes. The libinput test suite actually was really good for reproducing a lot of them. The reason is because it currently creates about 5,100 devices within about 3.5 to 4 minutes, and that's a really good way to test if the device initialization removal works in the server correctly. As I said, we fixed most of them. Expect that over the course of like 119, 120, we're probably going to run into more race conditions just as people use them. There's not much we can do about that ahead of time, I think. All right. In terms of input driver retirement, we are planning to retire Synaptics, Wacom, and all the other specialized drivers in favor of libinput. Historically, what we had FDev as a generic catch-all driver because it just handles every device as it is. And then we had a couple of specialized devices for specialized devices, such as we had the Synaptics driver for touchpads, we had the Wacom driver, we had the VM mouse driver, which is pretty much deprecated by now anyway. We had a joystick driver, and so on and so forth. What we historically also had, we didn't actually have a driver overlap for hot plug devices. So we always knew there was only one driver for specific device. So we never had to actually choose between drivers. Everyone wanted Synaptics for touchpads, everyone wanted mouse and keyboard, FDEV for mouse and keyboard, and so on and so forth. That has changed now. With libinput, we have a second catch-all driver that handles almost every device, but it's also preferred over the specialized devices. So specialized drivers. So libinput is preferred over Synaptics, even though it's a catch-all driver. So we suddenly have the hierarchy of drivers is slightly different. Exoc.conf.d or exoc.conf in general is just not reliable enough, flexible enough. It relies on the sort order, which is why things like FDEV, for example, starts with 10, so it sorts before Synaptics, which starts with 60 or something like that, and so on and so forth. And the only thing you can do in exoc.conf is you only have the command of like overwrite if matched. So you can say match on this particular thing, so product name, PID, VID, and so on and so forth. And if it matches, then you can assign a driver to it. But you can't say something, you had no negation, the match strings weren't particularly flexible, and so on and so forth. So it's pretty much like an impossible situation. What we added in the 1.19 cycle, I think, first of all, we have a no match support now. So instead of just saying match on this product, you can also say don't match on this product, which allows for things like you can write an exoc.conf snippet that says assign the Synaptics driver, but only if the libinput driver hasn't been assigned yet, or assign the Wacom driver, but only if there's no driver assigned yet, and so on and so forth. And more importantly, the X server now has a built-in fallback driver, which is something that, in retrospect, we should have probably done in about 2007 or something. But so what happens now is that if you assign, say, the Synaptics driver, but you don't have the Synaptics driver installed, the X server will just fall back to whatever built-in fallback driver you configured at build time. So if you can't find the module, it'll just fall back to libinput, for example. So at least that fixes the issue of if you don't have a driver installed, your device will still work. It just won't work with the particular driver you tried to configure. Again, in hindsight, we should have done that when we switched from mouse to FDEV in 2007 or 8 or whenever that was. We're also reshuffling the sort order. Libinput at the moment is 98, libinput.conf, so it just overrides everything. We shuffled that back to 40, which means it now sorts above FDEV, but it sorts below all the specialized drivers. And the long-term goal is that we just remove all the specialized drivers from users' machines unless they're needed. So in the future, the basic fixing of a problem is like, oh, my touchpad is still using the Synaptics driver, is like just remove the Synaptics driver and everything will just work. From an upstream point of view, that's fairly easy because we can just say this is how it's supposed to work, do it. From a distribution point of view, it's a lot harder because 99% of the users will still have Synaptics installed because it used to be the default driver. So you have to figure out, the distributions have to figure out a way of how to actually remove the driver from the user's machines. That could be quite interesting. It also means that if you don't support the XF86 input libinput yet, better get cracking, because GNOME already removed support for Synaptics, which causes some issues, for example, with Cinnamon and Mate, who both don't support libinput. So as soon as you install on Fedora, if you install Mate or Cinnamon, it'll force the Synaptics driver, at which point your GNOME touchpad panel will break. So you have to remove Mate again to log into GNOME, and it's just like a bit of a disaster there. Cinnamon now has patches for libinput. Mate is, let's just say it's a bit more tricky. If you have a desktop desktop environment and it doesn't support libinput yet, does not support libinput yet, kick your developers. Libinput has been around for 3 years now. Right, summary. On the technical side, we are approaching peak boredom. All the stuff I was talking about is not particularly interesting because it's just like, here's another hardware quirk, here's another hardware quirk, here's something that works now, here's something that works now, but there's no big features on the horizon that really get headlines. That's a good thing. Most sane people don't want their touchpad to be exciting. Yeah, that's it, actually. Credits. I've talked about, this wasn't all my work, it was mostly other people's work. So Benjamin Tissoir does a lot of the kernel work, both for the tablets and touchpad stuff, and of course all the multi-touch devices. Ping Zheng, Jason Garrick, and Aaron Skomra are the 3 Wacom engineers that do the Wacom kernel and also the Xorg drivers. Keith Packard did the input thread, so any race conditions you can blame on him. Carlos Garnacho does all the, or a lot of the GTK, Wayland stuff and GNOME stuff. David Herman did the Ratbag D, Dbus daemon. Nikolai Kondrashov for Digiment, the non-Wacom tablet enablement project, and Jonas Ordal for the relative pointer and the pointer constraints and all this in Wayland. That's it. Any questions?
What I noticed is that you have no slide about touchscreens. Is that...
True, I forgot about it. Touchscreens have worked since version 0 point something in libinput, and we haven't done anything to them, because all we need to do is pretty much you collect the touch point, you forward it on, and then all the hard work is being done by the clients. So we don't do gestures in libinput. We just let the client do the gestures on touch screens. So we do gestures on touch pads, but not on touch screens.
So will libinput also consider the Bluetooth keyboards and mouses?
How a keyboard is connected doesn't really matter to us as long as it has a kernel event node.
Okay.
So we do care about the connection status in some ways. So for example, for a couple of the features we only enable on certain devices. So as I mentioned before, the disable while typing feature disables your touchpads while it detects key events, so you don't accidentally move the pointer with your hand. So we disable that on Bluetooth keyboards, for example. We disable that on Bluetooth touchpads because they're external, you don't have that overlap. But other than that, we don't really care.
Currently, I'm having the interesting problem that I have a Bluetooth keyboard that works just fine, but not in the login screen, so I can't log in before I have the keyboard.
Right. That is inconvenient, yes. That is something, I don't actually know who initializes the Bluetooth connection. But that is something we can't work around in libinput because we need a kernel device to get the events that we then pass on. So whatever initializes the Bluetooth connection needs to get into the login screen.
You mentioned a couple of things where like there's a firmware bug in Synaptics and we can't really work around that. You sure about that? Like has anyone looked at, I know there are systems where like on Windows you can get firmware updates for your touchpad and it will blast something in, and suddenly, and in a couple of cases it's usually like, oh, I downloaded this firmware update and I downloaded it for the wrong machine and now my touchpad doesn't work. So if it's possible to update that firmware from the host side, and it appears to be on Windows, has anyone looked at like, can we find that for some systems? Is there anybody?
So Lenovo, which are the ones I'm most exposed to, just because that's what I have accessible, does ship firmware updates. We had on the 440 generation, they had a rerun and they updated the touchpad firmware. The X230 had a touchpad firmware update over the X220. And then some people installed that, so we have a UDEV rule that detects that particular device with the new firmware to initialize a special point acceleration. The thing with libinput is it's supposed to be a generic stack. So yes, we can tell people please update the firmware, but it's actually easier to just tell people not to do that and work around the bug so it works anyway, because detecting the firmware in user space is actually tricky. The kernel doesn't advertise it particularly well. So in some cases you pretty much have to pass the message, which we don't do. But so it's actually easier if everyone has the same broken hard firmware. It's a lot easier to work around it than if you tell people and then suddenly 10 out of 100 have the new firmware and we have to work around it in a different way. So in some ways it's actually better if people don't update the firmware. And sometimes, like with the firmware updates, so the T450 where I said like the cursor doesn't move, that is not a problem under Windows because the pointer acceleration under Windows is different. So users never move the finger that slowly. Therefore, they're not going to ship a firmware update because if it works under Windows, they're not going to fix it. Any other?
You mentioned the tablet pad protocol, the new API that you implemented. On which level it is?
On which, sorry?
On which level? Is it on top of EVDev, or is it in libinput, or is it in the kernel?
So pads are their own kernel event nodes. So if you plug your normal, like an Intuos, like the external Wacom tablets in, you get a pen device, you get a pad device, and you get a finger device, and there are 3 separate event nodes. And then the API for pads is in libinput on top of that event node.
Okay.
So you essentially get two libinput devices, one that gives you all the tools and one that gives you the pad interface, but libinput also provides a way to associate the two, so you know they're actually the same physical device.
Oh, all right.
Yeah.
All right.
So libinput has a concept called device groups, and any device that has multiple event nodes, any physical device with multiple event nodes, all these event nodes will have the same device group. So in user space, you know, or like any client of libinput will know, okay, these are actually the same physical device, even though we get separate event nodes for them.
How does it identify that they is the same device?
For 99% of the devices, we just use the syspath. But for Wacom tablets, we actually have on some Wacom tablets, the PID, VID, the vendor ID, and the product ID for the touch device is different than the PID-VID for the pen device on the same physical tablet. So, but with libwacom knows about that, so we can use libwacom to generate a set of UDEF rules that then changes the device group in libinput, so they both end up with the same device group.
Okay, thanks.
So, magic.
Thanks.
So a quick remark about the Bluetooth keyboard question. I think that it should work if you use GDM as a login manager and associate the keyboard with inside GNOME session, because then it will set some global key which GDM will pick up to also do the Bluetooth association. Of course, for the initial association, you need an actual physical attached keyboard, but I think that might work. And if you use anything else than GNOME plus GNOME, good luck.
Okay, no more questions. Thank you very much. I think it's lunch break now.
Yep, lunch break. Okay, so grab a seat, please, and we're about to start. So just a reminder that any kind of discussion that you're having here or ideas that you have, well, by basically being here and talking to the right people, you should try to make a lightning talk at the end of it. And yeah, so it would be on Friday afternoon, so you have time. We just expect one slide, and it's a 5-minute presentation. That's it. You won't have any more time. So more information is on the program page if you want. But yeah, please try to provide some, because it really is useful for everyone. And it's a good way for you to remember your idea also. Okay, well now we're gonna start with your presentation. Oh, you're not mic'd yet.
Can people hear me? Okay. All right. So let's start. My name is Iago Terral. I work for Igalia. I'm going to be speaking about the implementation of GPU shader FP64 for Intel GPUs. So this is how I would like to cover this. I'm going to start by making a quick overview of FP64 and kind of talk a little bit about the scope of the implementation. Then I'm going to focus on the implementation itself, which covers NEAR, which is one of the IIRs involved in the Intel driver. And then I'll focus on specifically on the Intel implementation, the driver level implementation, which I think is the most interesting part. So this is where I will spend more time. Now, this is very Intel specific, of course. I suppose not everyone here is particularly familiar with Intel hardware, so I'll try to make this a bit more accessible and explain a little bit how the hardware operates, at least the bits that are important to understand FP64. And I would like to wrap up the presentation with a recap of the current status of the implementation across the different hardware platforms that we want to support. So, about GPU shader FP64, this is all about adding new GLSL types for 64-bit floating point types. So this we have doubles, DBEX, and DMAT types, which we can pretty much use for anything we want, with two notable exceptions. One is 64-bit vertex attributes, which are covered with a separate extension. And then there is we don't have 64-bit from inside our outputs, because we don't have 64-bit format core formats for frame buffer objects anyway. So other than this, we support arithmetic and relational operators as we do with normal floats. And most of the built-in functions in GLSL also accept double types, with some exceptions that I mentioned here. There is also new packing and unpacking functions for doubles, conversions from to 32 bits. And the other thing that's special about 64-bit is that variants don't accept interpolation, so you need to declare them as flat. So this doesn't sound like it's a lot of things. We're basically adding a few new types, and that's it. However, the scope of the implementation is pretty large. This was combined work by Intel first and then Igalia for over a year. And as it stands now, covering Broadwell and Haswell, so basically Haswell and then Broadwell and later platforms, I count about 260 patches for this, covering NEAR and the Intel driver. And this is without counting that Ivy Bridge has more work queued up that will come hopefully soon. And this doesn't count work by other people who have been fixing things in the driver that helps FP64 in various ways, like Kuro's work on fixing spelling things, or more recently his work to enable sub-register offsets in the vector backend. So it's really a huge amount of work that has happening here. So the reasons for this are multiple. One of them is that this feature is useful across all shader stages. We have to implement it across various IRs, like NEAR, as I mentioned, and then the scalar and the vector backends in the Intel driver. It affects a lot of GL stuff that we can do, like algo operations, variants, uniforms, UBIOS, BIOS, shared variables. All these need to support 64-bit. And then there is a lot of internal parts of the driver that also need to be 64-bit aware, like optimization passes, liveness analysis, register spilling. So all these things, all these paths inside the driver need to be adapted to work properly with 64-bit. Now, it's not just about the scope of the implementation in Mesa, it's also about the scope in things around Mesa like Piglit. When we started working on this, there was already some coverage for FP64 in Piglit. It was mostly focused only on ALBU tests. But as I just mentioned, there is a lot more stuff to cover, and we added almost 2,000 new tests to Piglit to increase the coverage. And this was actually very important to catch things, code paths in the driver that didn't do the right things for FP64 that we wouldn't know otherwise. All right, so let's now look into the changes that went to NEAR. I'm going to cover this very briefly. As I said, I want to focus on the Intel-specific parts. So the big change that came here was the addition of bit size ALU types. So in the past we had things like NEAR type float, and now we have things like NEAR type float 32 and 64 alongside the original base type. This means that we need to be a bit more careful when we handle all types in NEAR or drivers that consume NEAR code. When we do things like checking for specific types, like in this little hunk that I have here, we are checking if a particular opcode, the output type for that opcode is a Boolean. And the right way to do this now is we compare it against the base type of the opcode, because the opcode could have a bit size type instead. So going forward, people should be aware of this change and think whether they want to compare against bit size types or the base types instead, something that we didn't need to do before. So other than that, or rather as a consequence of that change, there was a lot of work to do to make sure that every path in NEAR handled bit sizes correctly inside the driver and was delivering correct bit sizes to the Intel driver in this case. There was a lot of work also for making sure that we had the possibility to use to declare the bit sizes involved in algebraic expressions, for example, and validation to make sure that we got consistent and non-ambiguous bit sizes involved in these rules, that this was all written by JSON. And then we have new opcodes for conversions from and to 32 bits, packing and unpacking functions, and things like that. And the other big change that went to NEAR was lowering for a number of operations that were not natively supported by the Intel GPU hardware. So I mentioned here a few of them. Well, actually, these are all of them: Tron, Floor, Seal, Fract, and some others. Now, this lowering pass is available for any other consumer of NEAR that may be interested in implementing the feature and has similar restrictions. And basically what this pass does is for those operations that are not natively supported, it implements these operations in terms of 32-bit integer math usually, or other supported 64-bit operations. All right, so let's now focus on the Intel driver itself, which I think is the most interesting part. And some background first. So in Intel hardware, we have two backends, two modes of operation, which we call scalar and vector. I'm going to cover the scalar backend first, which is easier, and then I will go into the vector backend. So the way I'm going to do this is I'm going to explain how this works outside FP64 and kind of use that as an introduction for people who don't know the Intel hardware yet. And then I'll explain how things change for FP64. All right, so the scalar backend works on scalars. So what I have here is a representation of 3 registers. So the registers are 32 byte wide. So if you think them as a collection of scalar channels, they have 8 scalar channels per register. So Here we have an operation dispatched in SIMD8 mode, which means that we are processing data from 8 threads at the same time. So you can think of that, for example, from the point of view of fragment shader, where we have 8 fragments that we are processing in parallel, and we are processing one scalar element per thread. So what I have here is a simple move instruction where we are reading a certain number of elements, which are colored in yellow here, and writing them to the destination colored in blue. So the way this works is we start the start of our region. The region that we are moving starts at G1.1, so it's the second register, and one channel, 32-bit channel, because we are using a 32-bit type, a float type here, into the register. That's the start of our region. And then this ternary here tells us how we select the elements that we are going to move, starting at that point. And this is done as a collection of rows. So we have a 4 here, which is the width of the row, and a 2 here, which is the stride. So we take 4 elements with a stride of 2, all these in units of floats, so 32-bit channels. So we take 4 elements with a stride of 2, that's the first row. And then the next row starts 8 float elements after the first, so it starts here, and takes another 4 elements with a stride of 2. And we take 8 elements because that's the execution side, and that is here right next to the opcode. And then on the destination in blue, we do the same thing. We write at the beginning of the register file, G0.0. We write with a stride of 1, so we write consecutive elements, and we write floats, so we write the entire first register. Okay, so as you can see in scalar mode, we can pretty much address any scalar channel that we want, and we use strides to select the elements we want to operate on. So 64-bit is really the same thing. So in SIMD8 dispatch mode, we still have 8 threads, only that these threads now are twice as large. So we have 8 64-bit channels, each of which are 2 32-bit channels wide. Here we represent a DVEC4 worth of data. So we have the 4 components of the vector. Because we are on a scalar backend, we process each component separately because we only process scalars. So we have 2 registers worth of data for X, Y, Z, and W. So here is so basically getting double float operations to work is relatively simple. We just simply use a double float type to indicate that we are doing 64-bit operations, and that the hardware with that the hardware already knows how to interpret this ternary here, which it does in terms of the size of the type. So this would mean that it would take rows of 4 consecutive double float elements and then move 4 double float elements forward to take the next row. In this particular example, this would give us, since we start at G0, it would read the entire, the full 8 double float components that we have in yellow and write them in consecutive positions in the destination. And again, because it's a double float destination, it knows that it has to align the data to 64-bit when it writes. So in FP64, we have some access patterns to data that I think were not very common before. This can happen for a number of reasons. One of them is the login that we have in here for unsupported 64-bit operations, in which we produce 32-bit integer operations that access 64-bit data, typically because we want to operate on either the exponent or the sign or the mantissa of the 64-bit data. So in these cases, we need to produce regions that access either the low or high 32-bit of each 64-bit value. So what we see in this case is that we need 32-bit instructions. So here this UD here means unsigned decimal, which is an unsigned integer, 32-bit data type. And we will use horizontal strides of 2 to select just the low or the high 32-bit components. So in this particular example, because I'm starting on the second 32-bit channel, I'm selecting the high 32 bits of each double float. And when we write also in the second channel with a stride of 2. So again, we write only the highest 32-bit channels. Now this is a very common in FP64, but it might be necessary to do it also in other scenarios. And the best way to do this kind of regioning nowadays is to use the subscript helper that Core implemented instead of open coding this and adapting offsets, strides, and retyping registers manually. All right, so that was the SCAR backend, nothing very special there. Align system on the other side is a lot more interesting, as you will see. So here, the way this works is, again, for 32-bit first. So we usually use this with that dispatch mode that we call SIMD4x2. And what we have here is 2 threads instead of 8 like we had before. But we still operate on 8 scalar channels, but these are separated in 2 threads. Each one has a 4-component vector. So because of this, we can use swizzles and write masks directly, which is one of the big differences. But it comes with certain restrictions. One of the things is that the regions have to be system byte aligned. So they have to start at the beginning of a register or halfway through it. In this mode of operation, the hardware fixes the width of the rows to 4 elements, 4 32-bit elements for 32-bit. So what we have is 4 contiguous 32-bit elements, which is 16 bytes, which is half of a register that has to be aligned at the beginning of the register file or halfway through it. So basically what we are doing is selecting 4 32-bit vectors in the register file, in each register. So with a vertical stride of 4, what we are actually doing is beginning of a region that starts with the second register, we would be selecting in the first row the first 4 components, and in the second row the next 4 components. Now in SIMD4x2, the 2 threads are usually 2 different vertices, and what we do is we load data for one on the first half of the register file, and the other half of each register, and on the second half we load data for the second vertex. And within each of these regions we apply these 32-bit swizzles that we have here and these 32-bit write masks. So in this particular example, we would be selecting Y, W, W, W for each half of the register, so for each thread, for each vertex. And we would be writing only X and Y for each vertex as well. So here we use swizzles and write masks instead of playing with the strides. Now, Broadwell and later hardware used to require Align system support for tessellation and geometry shaders. But thanks to the work that Kenneth did, this is no longer necessary, and these platforms are fully scalar nowadays. Now, this was great for FP64 because it means that we only need to support the scalar backend to expose the feature, and there's no need for Align system. All the platforms, however, still require Align system implementation. So Haswell EV Bridge still need this for vertex shaders, geometry, and tessellation shaders. Okay, so why is Align system more difficult to get right? Well, one of the main reasons is that our swizzle channels are always 32-bit. So that means that if you have a DBEC4, you can only address half of it with these swizzle channels. Now, to make things a bit more interesting, even though the documentation suggests that write masks are 32-bit too, they are actually 64-bit, with the exception of 2 specific write masks that are 32-bit, which means that they don't have a native representation at all. So this is kind of a bit crazy, really. All right, so SIMD4x2 in Align system basically is set up like this. So we have, again, 4 channels per thread, which nowadays require, so that instead of, unlike 32-bit, requires a full register per vertex. So the thread boundary now is in between contiguous registers. Now, because of the 16 byte alignment restriction, the hardware seems to fix the width of the rows to just 2 double float elements, which gives us still 16 byte rows, which then we can address with our 32-bit Swizzles completely. But these 16-byte rows only cover half of a debug4. So with this regioning 2 to 1, what we get is 4 rows, which look like this. And well, if we now apply our Swizzle directly, this is intended to be CW in double float units. So what we want to select here is the second half of the debug4 for each vertex. But what we do if we apply this directly instead is to select channels C and W for each row that we produce, so we end up selecting something else. So this is not what we want. Another consequence of this is, if you think about it, is that we cannot represent all the Swizzles natively. So if we want to represent the replicated X Swizzle, we can't, because any Swizzle that selects X is going to select C, and so forth. The other problem that we have is, okay, we have to translate our Swizzles from 64-bit to 32-bit. That's easy enough for X and Y. X becomes XY, Y becomes CW. But what about C and what about W? How do we access this? It's not directly possible. So to avoid all of these issues, the first attempt at implementing this was to use component splitting and try to split debug operations into debug2 sizes, so we would only operate on just 2 components at the same time. So we would organize our debug4 data in register space a bit different. Instead of having X, Y, C, and W for each thread in the same register, we would have the first half of each register packing two 64-bit components, so X and Y in one register, C and W in the next register for both vertices. So we are recreating the thread boundary that we had for 32-bit somehow. And then when we actually need to implement an instruction, we would split it into 2 4-wide instructions instead, the one operating on X and Y. We just translate the Swizzles directly, nothing special there. The one operating on C and W would have to offset the register by 1 and then address C and W as if they were X and Y. Now the problem with this solution was non-uniform control flow. So the thing here is this happens when we have a vertex that meets a condition and executes conditional code, but the other vertex doesn't. So in this case, the hardware still thinks that we have 4 consecutive channels per thread. So it delivers this execution mask that I have here. So 4 ones and 4 zeros, meaning that we should execute the 4 channels for the first vertex and none of the channels for the second vertex. Now the problem is that our instructions intend to operate on 2 components for each thread, for each vertex at the same time. So when we execute something that attempts to read just X and write it somewhere else, it's going to do that for 4 components, but each of 2 components, each 2 components belong to different thread. So we end up moving X for both vertices because C and W channels for the first vertex are enabled. So this is definitely not what we want. So we are back to where we were before. We had to drop that solution and start over. And one of the problems we were discussing before is we need a way to address components C and W. And one way we can do that is, well, we can start our region at the 16-byte offset instead, and then translate C as X and W as CW. And if we were to do that, we would end up with something like this, which is a bit better. Now we select C and W, but we select a bunch of stuff that we don't want. Also, this would be invalid assembly because we would be violating some restrictions of the hardware. But we could probably fix that if we use vertical stride of 0 to limit the region that we select to just C and W, because that would replicate the row 4 times. Now the problem there would be that we wouldn't be selecting the right source data for the second thread, because we would only be selecting C and W for the first one. but we probably use SIMD splitting and have two different instructions, each one processing data for just one vertex to address that. Now, the interesting thing about Gen7 hardware is that it seems to have a bug that actually helps with this. It is that the vertical stride, when we set it to 0, is not respected for the second half of a compressed instruction, which for FP64 pretty much happens all the time. And so what happens is that when it decompresses the second half, the one that deals with the second vertex, it just ignores the vertical stride and always offsets a full register. So if you think about what happens when we do that, is that we end up with this regioning instead, which is exactly the one we wanted to use. So actually, when implement this in this way for Gen7 hardware, whereas if we were to implement this, that we don't need to, because now protocol and later are scalar, we would probably need to split the instruction in two. Now there is one more issue with this particular example I have here, and is that I mentioned before that the XY write mask is actually 32-bit. So we are not really writing 2 components worth of data, and we are only writing 1, which is again not what we want. And because there is no native representation for this write mask, the only way to deal with that is to end up scalarizing anyway and split into instructions, one write into X and one write into Y separately. But this should work. Now the problem is this was just one example. I mean, there are more Swizzle combinations you can think, for example, on cross-DBEC2 Swizzles that would require different strategies to be implemented. There's also instructions with 2 or even 3 sources, where each of the sources involved in the operation might require different strategies to deal with the Swizzles they have. And when you apply these strategies, you can end up in a situation where you may need to review again the Swizzles involved and see if you have to again apply any techniques, or you end up with a write mask that is one of the 32-bit write masks, and again you have to split because of the write mask. So we thought that just trying to deal with all of these upfront would be a bit difficult, and it would postpone having a functional implementation. So instead, we decided, maybe in the end we end up having to scalarize a lot of this stuff because of all these restrictions. So why don't we just scalarize everything up front, and then we try to build up from there and improve things where it makes sense. So that's what we did. The first step of the implementation is scalarize everything. That gets rid of the problem with the write masks completely, because you only have one channel write masks. It reduces the number of Swizzles you have to deal with to just 4 Swizzles, which are easy enough to implement. X and Y, you just translate them directly. C and W, you use the trick that I mentioned before, and that's it. There's one thing that's important though, and it's that the Swizzle translation for 64-bit to 32-bit, we do that, or we want to do that after, as late as possible, so that the optimization passes and things like this don't need to know about all this crazy stuff that happens, because otherwise it would be really mad to deal with all that. So once we got that working, the second step is, well, there are some Swizzles that we can implement natively. Basically, any Swizzle that selects the same parts from each of the 2 rows that cover an entire DBEC4, this we can implement natively. So X, Y, C, and W, for example, is meant to select the full DBEC4. So that's exactly what you select if you apply the 32-bit X, Y, C, W Swizzle to each of the 2 DBEC2 that you have. So this we can do directly. The next step is you can exploit the issue with the vertical stride a bit further and use that to implement replicated Swizzles, for example, because now, thanks to that, you can limit the Swizzle to just one DBEC2 chunk. And if we want to go further, we can also do that, but it would require to look at the Swizzles involved and think how you can split them in ways that you can implement following these strategies. With the caveat that, as I said before, that could be a recurring problem and, with the write mask and with the other sources involved in the operation, and you may end up scalarizing more than you were hoping for. But we haven't done this yet. We are hoping to kind of get all the other bits well and done, landed, before we attempt to do this part. So that's kind of the basics of how this works for both backends, and then there is a lot of other stuff that goes in between all this. One is that, as I suggested before, there's significant differences across the hardware platforms that we have been working with. So EVBridge, I think, was the first to support FP64, and it has some annoying things, like the fact that the ternary that describes the size of the elements that you actually select, the regioning, is in units of 32-bit always. So that means that you have to duplicate the parameters and the execution sizes, which again you want to do as light as possible to not mess with the bulk of the driver. It's also a lot buggier than the later generations. Haswell got the regioning right in units of 64-bit and then improved a bit. There's a few less bugs. And then Broadwell, we can do scalar there, so we just forget about the crazy align system stuff and we just do scalar, which is great. And Skylake was the first platform that we didn't have to do anything special for, so I hope that future hardware doesn't require a lot of tweaks to get things working. So other platforms such as Braxton, ShareView, or Braswell, they only require really minor adaptations, so that was fine. So another thing we had to deal with is the fact that before FP64, all GLSL types were mapped to 32-bit types in the driver, and that meant that we were free to assume that the sizes involved in the operations were always 4-byte, which now it's not true anymore. We also assume in a lot of places that the strides that we use were just 1, which is not true anymore a lot actually in FP64. So we had things where in this hang that I have here, we were computing the size of a destination, the number of registers that we were writing, and we would do that by dividing the execution size by 8, which is implicitly assuming 32-bit types and a stride of 1 on the destination, which breaks for FP64. So the right way to do this going forward would be to use these helpers like component size that take into account all these parameters to get things right instead of open coding these kind of computations. Now the problem with these things is they were difficult to track, and that's why we wanted to have good piglet coverage, so that piglet would tell us what paths were broken because of things like this. So as I said before, there is a lot of new, well, not so many, but there are new code patterns that we push with FP64 into the driver, like horizontal strides that are not 1, access to the same register with sizes of the types that have different sizes and different instructions. And some of these really drove some optimizations passes crazy. In particular, copy propagation got patched at least 7 times to fix different things that didn't like at all FP64. I wouldn't be surprised if there are still more bugs related to this. Okay, another thing is the GPU only has 32-bit read and write messages. So for all things that involve memory access like UBIOS, VIOS, Scratch, URB, things like this, we end up having to do some special handling of 64-bit paths. And I think it's better explained through an example. So we are back to the scalar backend. And remember, we have this 32-bit, so we have 8 32-bit channels that we are processing in parallel. And for each channel, we want to emit a read. So we provide an offset. We read data from each channel's offset. And then the GPU will write the result back into register space. And it reads 16 bytes, so a back4 worth of data for each thread. And it writes it, just like we want in 32-bit. So each 4-byte component in a separate register within the same channel. So this is how we want things for 32-bit operation. However, in 64-bit, there's 2 issues because the GPU can only read 16 bytes. At time we need to emit another read when we have anything larger than a DBEC2, of course. But then the other problem is because they are 32-bit messages, our 64-bit data is channeled through a 32-bit channel, so we end up with the low and high 32 bits of each 64-bit component in separate registers, which is not what we want, and we need to shuffle this data back into valid 64-bit data that we can use. Now, when you want to write, you start from this situation, and you want to prepare data like this before you write to memory, so you have to do the inverse operation. So another thing is there's no support for 64-bit immediates in Gen 7. There is some support for this in Haswell. There's a specific instruction that we can use for that. But EVBridge doesn't even have that, so we have to kind of load using 32-bit instructions manually into virtual registers, and then using corresponding swizzles and strides depending on the backend to make sure that we address the correct data. And then there is a number of either restrictions from the hardware or bugs affecting both Align 1, but especially Align 16, where, well, usually, I don't think I have time to go through all this in detail, but the basic common denominator is that FP64 at least has a lot of issues with compressed instructions, so that we either get wrong execution masking for the second half of the instruction, or we get it doesn't do the right thing with the predication mask in some cases, or it ignores the vertical stride, as I mentioned before, or things like that. Now, the good thing is that the solution is pretty much always the same, which is to split the instruction so there's no compression involved, and that works. So in the case of the Scalar backend, where we already had a SIMD splitting pass, this was just a matter of adding the new situations in which we needed splitting for FP64. For Align 16, we didn't have that infrastructure in the driver, so we had to create a new pass for this. And yeah, so to wrap things up, current state of the implementation is we have already shipped FP64 with Scalar and Broadwell. This was thanks to the fact that we only need the Scalar implementation for these platforms. Haswell and EVBridge need Align 16, which has been in the works since then. So for Haswell, we have working implementations of shader FP64 and also Vertex Drift 64-bit. For FP64, we send the patches for review, a first version of it, and we got feedback. We are working on it, and we will send Vertex Drift 64-bit probably after FP64 is in good enough shape to that. As for EVBridge, we have also been working on that. We have the Align 1 backend adaptations ready and seems to be working. And Align 16 is a work in progress, but it's nearing completion. So there's only a couple dozens or 3 of pilot tests to go, I think. And the only thing that hasn't been started yet is Vertex Drift 64-bit for EVBridge, because we want to get FP64 ready before we start getting... I don't think it's going to be a lot of work after, or a lot of changes from the Haswell implementation, hopefully. And that's all I had, so if you have any questions, I'll try to answer. I guess I was very clear.
So how's the rest of it going? I mean, there's still a few things left to do, and I mean, there's a bunch of stuff that's in review. Is it?
Oh yeah.
Do you foresee more pain?
No, I think the hard part, especially for Align 16, was to understand how the hardware actually worked. I remember the beginning was quite painful because yeah, there's these bugs, and I have actually a slide here where you were trying just to get the basic thing working, which was a simple shader that would load the uniform and just write it to the output, and you would hit 2 bugs, and it was like, this just doesn't work. But once you figure out what are the actual problems, and Kurt was super helpful, giving us solutions and suggesting things and testing things for us. So I think once you got that, I think it was fairly easy to go forward. And now I think we got some feedback from Kuro on the patches that we send. But I think at this point, it's should be all straightforward, I think.
Yeah, you guys have done really, really great work. Thanks.
Thank you. Okay, so if there are no more questions, I guess we're done.
So we're going to start again. But before this, I would like to remind you to register for the post-conference social event on Saturday. So as a reminder, it is like a short visit of Helsinki, and then just going to a sauna and into the sea. I mean, the true Finnish style. So yeah, and please write your name at this Frama date here, which is like Doodle, but an open source one. And yeah, so please do this. And tonight after 5, this is done, and I'm gonna start planning the event based on this. So yeah, if suddenly 10 or 15 more people arrive, there's no way it's gonna work. Okay? So please register. Okay, then we're gonna go to the talk. So I am Martin Perez, and I work with Intel OTC. So please get out of there. So Intel OTC in Finland. And I'm going to talk about 2D performance. This is something that I've been interested in sort of recently because of the effort to study mode setting and see if we could move to it. So part of the equation is definitely performance and trying to understand where we have shortcomings and how to and what we should do to fix them. And that led me basically to this evaluation and discussion. So because not everyone knows here about what is X, well, or what it does basically, and who is using what, I just decided to just make a short introduction. This is a pretty short talk actually. And so there is a short introduction to it, and then before we go into data basically, and then just a discussion about it. Okay, so well, the X11 protocol is pretty old. I think it's more than 30 years old now, 32 something. So the idea was that an application would connect to an X server and request the X server to render 2D primitives to a buffer. At the time, it was, well, obviously done by a CPU because no GPUs existed. And when GPU appeared, at some point, we did get these primitives accelerated. And at some point, someone figured that, well, the primitive set was not really matching what applications wanted to do, so they introduced the XRender extension, which added a lot of primitives. So who is using these primitives nowadays? So there is the very old, well, basically Motif and old toolkits, which would be XT, X toolkit. In this case, all the rendering is done by the X server. Nothing is done in the CPU on the client side. Then you've got GTK, which is what is being used for GNOME, and they use Cairo for all the rendering, and Cairo in turn uses the X server. Then Qt, which is the base of the KDE and desktop environment, uses basically the CPU nowadays for everything client side, except for anti-alias text and cursor alpha blending. This is from the wiki page. And for everything else, it either uses the GPU or the CPU. So it has its own scene graph and everything. But there are also, of course, applications that do talk directly to X. They are pretty old, usually, like XI and all the small applications that you would get bundled with Zorg or Xterm or all these very, very old apps. Yeah, but applications should never use the X11 API directly. I think there is a warning for this in the XLib documentation. Do not use this unless you're a toolkit, and please talk to us. Okay, now performance evaluation. So I did evaluate this on the Intel platform, Haswell GT2, which is supposed to be very well supported by the Intel driver, and works also on mode setting, and I just know that it works well because that's what I'm using every day at my desktop, on my desktop PC at Intel. So I updated everything to Git, so I'm using the X server and the Intel DDX from Git, and it was on the 15th of September that I last updated it. And for Mesa it was the day before. The power is read through RAPL, which is software model that runs inside the CPU to, well, basically, okay, it's like having small performance counters saying how many times did I have a cache miss or cache hit or something. And these operations basically have a cost associated to them. And then there is a model of how physics would make the electrons go through all this and basically end up with a model of the power consumption. And I've tested already that it works pretty nicely on this on this platform at plus or minus 5 watts. So for the purpose of this presentation, it's going to be good enough. Then benchmarks. Used Cairo demos and traces because Cairo supports both, well, CPU and the X backend. That means that either it's going to use its own rasterizer client side, or it's going to use the XLab to talk to the X server and have the accelerated primitives from X. And this is what I want to see, basically. How much acceleration we're going to get from X. So the first one, let's start with the Cairo demos. What we can see is that the fish demo is actually pretty good. The values that you see here are normalized value. That means that XLab is the value, 1 would mean that the XLab backend would be as fast as CPU, and if it's 2, then it means it's twice as fast. So in this case, for the fish demo, it's 32 times faster. Looks like a pretty good acceleration to me. And as for the FPS per watt, which is the power efficiency, we can see that there is a factor of 15. So definitely in the case of the fish demo, the X server is doing a tremendous job and accelerating everything and using way less power. Okay, all good. Then we move to other ones. And the chart one is already not as good because there's a acceleration factor of 3, which is not too bad. But then the FPS per watt ratio is just 12% better. Still better, better than 1, but yeah. And then we go to the Tiger demo, which is half the performance ratio, and now we are just 50% faster. It's already like, ugh. For an acceleration framework, it's not super nice, and actually does a worse job at the power efficiency. So this is on the Intel DDX, which is probably the most optimized driver, or one would hope so, given that it contains 200,000 lines of code. But I wanted to know what mode setting would compare to, and we can see that in the case of the fish demo, which is just basically compositing fishes on an aquarium, which is not exactly super hard, it actually works pretty well. We get same kind of acceleration, same kind of FPS of efficiency, but as soon as we go to the second one, the chart demo, it already is pretty bad. AKA, well, the efficiency is 40% less than what you would get from the CPU, and in the Tiger case, the acceleration is just 16%. So this is just 3 data points for 2 different drivers. Now we're going to have a look at traces, Cairo traces. These traces come from real applications from 3 years ago. That's basically the latest update that was there. And we are going to check how basically they perform and what power efficiency we get out of them. And this is really why I chose Cairo. It's because there's so many GTK application and Cairo traces, and the fact that we can select that runtime, which backend we want to use to replay the trace, is very valuable for doing this evaluation. Okay, so every bar that you see here is a different demo or a different trace. I ordered them so as they would grow from the worst to the best. The red line that you see is the parity line, which is 1. That means that the XLab backend would be just as fast as using the CPU. So in this case, this is Intel, and there are basically 2 cases that are half the performance of the CPU backend, but most of them are better. But it's not amazing like we saw for the fish demo. Here we just have up to 3 times the performance of the CPU backend. But it does accelerate a bit. Now let's have a look at the power efficiency. Now we can see that most demos actually, most traces would actually use more power than using the CPU. So this is problematic because performance nowadays of 2D application is not an issue. So what you really want is to save power. And in this case, what we see is that from purely a power point of view, it is not helping to use the GPU at all. And this is understandable because there's no throughput. So GPUs are meant for throughput. They are not meant for very small operation like draw 3 pixels here and then let me fire a new pipeline to just write a line here and small, I don't know, circle. So this is no wonder that we do not get any kind of real acceleration. So now we're going to have a look at the mode setting driver. Well, this is not this is not very nice. Basically, we get from 10% of the CPU performance to 23%. To 2.3 times more. So this is what has been bothering me a bit about moving to mode setting. But then, when we talk in the discussion, I think that I'm very hopeful that mode setting has a real future. So energy efficiency wise, it's just the same story. It is, I mean, this case is just the worst. That means that the CPU backend would use 3% of what would consume XLab basically when using X. So this is clearly there's something wrong, and so this is where we're gonna talk about basically what toolkits are doing. And nowadays, Toolkit cannot rely on X being running on Linux because there is Wayland, because applications want to render on KMS directly. This is something that the automotive industry has been interested in. It means faster boot time, one application, low latency, all this. So since toolkits cannot really depend on X anymore, like X being present and running, and since, well, they're already moving to having their own CPU and GPU renderer, then does it really make sense to keep on pushing and really spending a lot of engineering time on fixing or improving mode setting and adding complexity and making it less maintainable in the process? Or is it better to... sorry, I got carried away. I went too far. So this is basically what I was saying. Since the acceleration is so little compared to the CPU renderer, unless you're doing composition, in this case it's really good, but composition can be done very easily client-side using GL, so it could be okay. It also uses more energy than the CPU in most cases, even on the SNA case. So it is not a mode setting issue, it's more like a more global issue of basically firing very small tasks and writing the task to a small, to a buffer, sending it in a socket, and then on the other side reading it and then sending it to the DDX, which is gonna, start make GL calls to fire a task that is just gonna write a few pixels and then just wait for it to be done and then return back all this. So that's so much operations rather than just writing the pixels using the CPU. I mean, this is Intel hardware where basically the CPU has easy access to buffers. But yeah, I think this is a valid case. And yeah, so rendering 2D also is, as I was saying, is not. If you use X to render on Wayland, that's a bit funny. Or on KMS only application, you cannot really depend. Toolkits need to have their own rasterizer, and I would, and also it doesn't support 3D transformations. So toolkits are already moving away from it. Qt has its own CPU renderer, as I was saying before, and GPU acceleration, and with QML they use OpenGL to do composition of the different widgets, and they support 3D transformations and everything that CSS supports, all is there. And GTK is basically now doing the same. It's called GSK. Right now there's only the composition. They still use Cairo to render every widget into a different buffer and then do the composition on the fly, and they can do basically all the CSS transformations on this. and they are very happy about this, and now they are moving forward and actually actively working on using the GPU to do the rendering. And yeah, I'm sure you also heard about the Servo project from Firefox, where they do get a lot of GPU acceleration for CSS transformation by having their own well, acceleration framework that they implemented themselves. So yeah, in light of all of this, shouldn't we tell applications to start using client-side rendering? Why talk through sockets to servers to do rendering when you can just use GL or even the CPU for the old applications? For the CPU, yeah, you can use Cairo or Qt or GTK is using Cairo, so yeah. Of course, if you want to use Qt for doing 2D rendering, it's going to be bad unless you actually want to use the entire framework. But on the GPU side, there's Kia from Google, which is absolutely terrible to use because there's no external library. It is static only, and but I mean, maybe someone would be interested in taking the code and making it a real open source project and having a community around it. Yeah, or there is a new project also started from Intel, and this is the FastUI Draw that is going to be presented by Kevin, and I think it has future for basically all the cases that I was saying before, automotive industry, and where they need to have 2D and they don't want to deal with OpenGL themselves, and yeah. So what is your opinion on this? I think we need to get mics. Oh yeah, second one is here.
So one of the weaknesses of using Cairo traces for comparing CPU to XLib performance is unfortunately that Cairo traces runs your trace to the point at which you need to upload it to the GPU.
Mm-hmm.
And if you're already running things on the XLib side, your stuff is already on the GPU and ready to be potentially scanned out directly. And so when you do CPU to XLib performance comparisons, it's always a little bit unfair to XLib because your stuff's still sitting in the wrong domain.
I see. Yeah.
So, yeah, those graphs are bad. We should fix them. We've never done the traps acceleration in X. We have real shaders now. We could just do that. It would be great if somebody actually worked on that.
Done what? Sorry?
Traps.
Traps.
The basic rendering primitive that Cairo uses in XLib.
Oh, okay.
It's all in software on the server.
Oh, well,
render it in
that may
software,
explain.
put
Yeah.
it in the texture.
Okay.
Somebody should just write that shader. It would be
Okay.
really nice.
So that would be very beneficial indeed. So, but it still doesn't change. I mean, this is for mode setting. As for the Intel TDX, then you would expect that. Oh. Okay.
One thing that's also sort of missing from this is, like, yeah, you can see that clearly there's efficiency problems in the mode setting driver, which I assume this was all using Glamour and not using the software
of course, yeah.
version of mode setting. That would have been an interesting data point. But if you're using Glamour, a quick read through Glamour, I just checked this to make sure this is still the case. Every time we call block handler, which is to say every time that we are done processing requests or switching between clients, we call GL flush.
Yeah, I guessed so.
We don't need to. It's super easy to just like not do that. So when you say, yeah, mode setting has these problems, well, yeah, we're doing a whole bunch of stuff that's much more serial than it needs to be. But I also can't really tell. I can guess from looking at that graph that the reason why you're seeing a tenth, less than a tenth of the performance. Yeah, that does sound like you're doing a lot more work per round trip. But without actually drilling down a little further into that, I can't see where that shelf is. My concern is if I compare that graph to the SNA graph.
Yeah.
I bet that I can get mode setting real close to 1 all the way across the board. And as somebody who works on an enterprise operating system, I can't tell Motif to change their rendering primitives. So I'm going to need a mode setting driver, or I'm going to need Glamour, be that on mode setting or under X Wayland. One way or the other, I've got to make those work, and I can't have it fall through the floor. yeah, we can talk about is it beneficial in a lot of cases to do rendering on the client side, but you know, if you're not, I have to support rendering over the network, and I have a set of primitives that I have to keep rendering it quickly anyway. I think it's much like telling every toolkit to adopt client-side rendering only works if we've got a solution that's ready to go. GL isn't that, because GL is really hard to use in a library context. Vulkan isn't that, because Vulkan is, let's call it an 0.8 level technology. I can't tell people, you know, and if your rendering primitives are Core X, I don't have a library that's ready to go and ready to consume on the client side beyond, and actually Pixman isn't this, because Pixman can't do lines, it can't do arcs, it can't do things that you don't want to do but that your application might have.
Yeah.
So I can't say use this library instead. I can't even say set this environment variable and libx11 will transparently render this on the client side and push images across instead. So this is an interesting finding, but I think there's some data missing, and I think there's some easy work that we can, like Eric said, there's some easy work that can get us a lot closer to unit performance there.
Yeah, but even if we did get close to SNA, which I was considering as being the optimal in the case of Intel. Okay, so what Eric said is that we should be able to crush it. So okay, very good. But do you think that it really is going to be at least a factor of 2? Because acceleration, I mean, CPU to GPU, I would have expected a factor of 6, 7.
Define acceleration, though. One of the things to remember is that if I'm doing all this, if I'm doing my rendering on the CPU, that CPU time that the rest of my desktop doesn't have, you have this coprocessor that's designed for this thing. Its front to back performance might be slower than doing it in the software, but if it can be processing things asynchronously and my CPU can be doing the rest of my, I don't know,
but did you
layout
check
engine,
the CPU usage? Because in my case, every time I was running stuff with mode setting, it was using 100% of the CPU, just doing stuff in GL.
That's also, I mean, that's probably fixable. Again, there's not, that data is absent from this analysis.
Yeah, yeah.
And yeah, queuing up lots of tiny little batch buffers and flushing them out every single time is going to take a lot of CPU time. But that's the trade-off of yes, the reason why you have acceleration, even if it's only 20% wall clock faster, you want that CPU time so that you can do page layout in Firefox while you're doing rendering on the GPU.
I fully agree, yeah. But then from a power perspective, then this is really problematic because...
No, it isn't. Again, if you have those two chips lit up and they complete 20% faster as compared to running it all on the CPU where you have to do all your page layout in software and then all your rendering in software, that's the head-to-head power comparison that you need to do, and that's what you haven't done here at all. This is if you were to do that comparison, what you should be doing is testing against mode setting with Shadow FB.
Okay, yeah, that's definitely an interesting data point. I should definitely try this.
Because the Shadow FB path is we're not touching the GPU at all. It is not doing anything other than shoving.
Yeah, so that would be the worst case scenario, and we would check actually what is the overhead of the communication with the X server, and then, yeah, this is definitely an interesting data point. Yeah, definitely agree. And I also agree with what you said, that applications are the way they are, and we need to make sure that they perform reasonably well. I was not saying the opposite.
I wasn't trying. I'm sorry if it sounded like I was accusing you of that.
No,
I was just
sure.
emphasizing I can't change some of this aspect.
Absolutely, this is true. I was just, when I was saying that we should advertise that maybe applications should move to client side, is more like forward-looking and just being, well, we know that we want to phase this out, basically.
So one thing that is possible there, and I kind of hinted at it, is we've got FB. We have the software renderer. There's no reason that can't be a library that libx11 itself consumes. And if you want to run your application in some mode that says, yeah, I'm going to mostly do this on the client side, and most of my X resources aren't actually there, and I'm going to draw on the client and just do image pushes whenever things need to show up. That's a thing we could add to XLib for people that need libx11 compatibility. There's no other way I'm going to get that change in motif. right? There's no other way I'm going to get XAW applications to
But
do
motif,
that.
motif applications are fast enough. So
I mean, granted, you're only doing Cairo traces here, but the complaint that we've heard in a couple of cases is no, they're not. That if you use Glamour, that you spend enough between, if you do fill arcs between in software, you build this mask, you very slowly push it through, writing like one span at a time through GL, and then flush when you're done with that. When you are done with that request. Between those two things, yeah, you do end up being wall clock slower, just for the pain, just for the cost of transitioning to Glamour as your backend. So, no, they're not. And if you measured probably X11 perf, you could have found this in a bunch of cases where, yeah, the wall clock performance for Glamour on Core X operations is slower than FB. Again, those are fixable, and there's not that many GL features we would need to wire through Glamour to make that happen. But only looking at Cairo is problematic for a lot of reasons. Cairo is also a bad rendering model. So
yeah, but I haven't found any other case where I could be comparing the two. So this is I took what I could get.
If you would like to know some more cases of like tests that are interesting, we can have this conversation all day long.
Yeah, we need to. And also with Eric, because apparently he has, Eric and Keith, I guess. Yeah, definitely. Okay.
But this is good data. And it's good to see it, and it's good to see that we're only within a factor of 10 in the worst case. That's cool. Like, honestly, I'm glad that it's only within a factor of 10 for Cairo. That means we can probably get to within a factor of 1.
Okay. Someone wanted a mic, yeah?
I think that the slides are missing one more important data point. Basically, you have benchmarked the Intel driver, the Intel X driver, and the mode setting X driver. But more and more important for compatibility reasons would be to measure the performance of X Wayland on top of, for example, Western. I expect it to be quite close to mode setting, but maybe there is some overhead that we don't know.
Yeah, but this is true that on X Wayland there may be more overhead, but I was more thinking about doing the rendering as part of X.
So going back to the should we tell clients to do direct rendering, I previously was in the we should be telling clients to do direct rendering camp, and Keith had brought up a good point to me, which is our GL drivers are really huge and slow to start up. And it's really nice to have a centralized server in the system that has already compiled a lot of the shaders you're going to use and has already eaten that memory overhead of bringing up an entire compiler. So yeah, Firefox should probably be drawing with GL directly, but possibly my Emacs shouldn't be.
Yeah, that is indeed a fair point. Yeah.
But GL also doesn't have some of the, like, how do you, there's not a global GL cache of all the fonts pre-bit mapped out to the resolutions you might like. X has that in Render. It's one of the few things that Render does well. That can be a very large amount of data that you'd rather not share across a system. Now, again, do we want to optimize this other thing too? Would we like GL context initialization to be fast? Yes, absolutely. But there is not no benefit from having a centralized rendering server.
Yeah, it would be cool to put all this in one page and explain this situation, because 2D has been basically not much has been happening in the past 3 years,
and you know, having a rendering server means you have threading for free. You know, if you're Firefox and you already have a complicated enough event model that you have multiple threads, then that doesn't really win you anything. But for a trivial application to just be able to hand off a batch of rendering and get back to its main loop, that's a nice feature too. Otherwise you have cores that are just sitting there not doing anything.
Yeah, I mean, text is really the killer feature for the core protocol right now. The fact that we have a single location that shares textures that contain all the glyphs really means that you're using a lot less memory in the system for text. And if you look at what we do, the problem with the traces here is you have 90% of these are graphics intensive traces, and 99% of what I do on my screen is text. And so really, instead of looking at a spread of operations like this, you really need to weight them in terms of,
Yeah.
oh, these are important, these are not.
Yeah.
When I did the original analysis for building the little acceleration architecture in K-Drive, I did profiling of applications, and applications in that era did three things. They did solid fills, they did scrolling, and they did text. And if you accelerated just those three operations, you did 99% of what my session did, which means that, of these 60 tests you have here on the screen, probably 0 of them are relevant to what I do day to day. And so we need to make sure that when we focus on, when we talk about accelerating 2D operations, we actually accelerate things that are relevant. The big change between now and then is that now we have a very browser-intensive environment, and there are a lot more graphics. I don't know what Firefox is doing for graphics these days. I suspect it's mostly images. And so
Yeah,
I do not see a lot of geometry in my world. And all of the Cairo traces are hugely geometry intensive. And that just doesn't exist in the real world today.
Well, there are many Cairo traces about websites.
Yeah. But, those are using websites that are doing things like, they're actually drawing
Yeah,
stuff.
they're probably intensive, as you say. Yeah.
Right. And so it's just not representative of what applications do. And so if we can get to the point where we have some actual way of benchmarking what a typical, like capture a rendering trace of your day at the screen.
Yeah, I wish we
Right?
could.
We can.
We can, but then we couldn't be running the difference, like how the CPU would perform. So that's the problem. Yeah, you can trace operations that have been sent, and then you would have to recreate a demo out of this. But I guess it's possible. Yeah.
Yep. So, and what do you want to get out of this? Do you actually like Ajax was talking about, doing client-side software rendering for Xlib? Who cares? Xlib is pretty well, the things that Motif does today, which is not render, just all of the core X stuff. Glamour does that awesomely well these days. And the Cairo tests are not going to show any of those. But if you look at like 2D lines, 2D text, 2D arcs, all that stuff, Glamour just completely blows software out of the water on all those things. And so for his Motif applications, we fix Motif. Motif is solved. Motif is plenty fast and uses very little power now.
I did actually say that is not uniformly true. That there are cases where arcs and wide lines do not go fast enough. But I also said that those are straightforward to fix. And if you are the sort of person who is still running them, you are probably also the sort of person who had enough hardware budget to buy a graphics card with the GL features to accelerate them.
Yep. Yeah, because you need a card from 2016 to accelerate your application from 1980.
Okay. Well, we're already 7 minutes out of it, so. Okay. Very quick.
Yeah. So, and that's the other thing is that we spend a lot of time optimizing GL drivers for an entirely different kind of usage pattern, and there's probably a lot of low-hanging fruit CPU usage where we're just doing things dumb because meh.
Yeah.
Yeah. That's the kind of thing that would be a really good project for someone to look at how some of these traces going through Glamour use CPU time in the GL driver.
But there is one thing that is really hurting this 2D performance project, is that it's really difficult to measure, and there's few customers who would be really like, hey, we need this. At least I'd never heard about them. Apparently Ajax has, which is very good. Yeah. Okay. Very good. Thanks for the discussion. That was really helpful. And we should try to have a small discussion about what's next, basically.
It's a fake pocket because I'm cheap. Can I be heard clear? Yes, I can. All right. So, at the risk of more controversy, I'm going to introduce a something to draw 2D content that's been built from the ground up for GPUs that draw triangles. I just want to emphasize why I say draw triangles, because there's other forms of video accelerators that don't talk about triangles either. Okay? So first off, what I want to stress also is that the way the current renderers are, they automatically limit our workload. We're willing to threat them. You don't want to rotate. You don't want to clip against interesting shapes. And you don't want to rotate and clip at the same time. You have to be careful about your text. You don't want to rotate, skew your text either. You have to be very conservative. What a lot of solutions are is, okay, we don't do any rotation, skewing of our content. We'll render it first to an off-screen buffer, and then we'll rotate and skew that off-screen buffer, the blit. I'm not comfortable with that solution. It's kind of hacky. So I made a benchmark that could be claimed as entirely artificial. It's called painter cells, and it's very simple. There's a blank color background. There's a table that's rotating and moving. Inside a table is a bunch of cells. Within each cell, there's a rotating and moving image. There's a rotating and moving line of text. The boundary of each cell is stroked, and each cell is rotating independently. And then you can configure how many cells you want to run. And the interface made in FastUI Draw mimics what we expect for a standard Canvas style interface. So your transformations, set your clipping, this kind of nonsense. And it's ported to Qt, Cairo, and Skia. The project's totally open. So there's a GitHub page I'll show at the end, and there's a branch where this stuff is with ports of painter cells, hopefully even spelled correctly. And this is what a typical screenshot looks like. Zoomed out. Okay. So these are the performance numbers I got on this laptop with whatever configuration it's on. It's an Ivy Bridge box. And the values are normalized to the Cairo CPU. Now, I trust the Cairo CPU backend much more than the XLib backend. I've noticed rendering issues, especially on dash stroking with the XLib backend. Okay? So these are all these numbers are normalized against Cairo CPU. And another really important one that people don't like to use a lot outside of Chrome is Skia, because that is probably the most widely used 2D renderer in the world. It's on every Android and Chromebook device. It's used every time you launch Chrome. That is the one whose performance you should watch. If you have a solution that performs better with similar visual quality, then you have something. And Google does do good work with Skia. So here are the numbers. One of the most interesting facts is the GL backend is almost 4 times slower on this load. The XLib backend is faster, but it does weird things to my desktop while running. And then also here is Qt. And we see Qt, its raster backend is almost the same thing as the Cairo CPU backend. The GL is slower. The native, which Qt maps to X, is incredibly slower. And then we have the Skia GL backend, which is almost twice as fast. And then we have the FastUI Draw, which I stress is experimental. It's not stable. It's not productized. 9 times faster. What happens when I put more cells on the load? Then we see the GL backend for Cairo fall even further behind. The XLib is not as high performance advantage as it was before. Qt raster is now going faster than Cairo CPU. GL, not very good. Qt native is really bad. Skia GL loses some of its advantage. And that which I've made increases its advantage to a factor of 11. One of the things I want to stress is I want to draw complicated stuff on the screen. And I don't want to ask a user to say, well, you know what? You want to draw something interesting with SVG, you're going to have to do it yourself with GL or Vulkan. Good luck. When in fact, these interfaces have been around forever. We should be able to have these interfaces draw complicated, interesting content and perform well. So why did I do this? Well, how did I do this? I did not cheat. I want to stress that. In some situations, I have better render quality than Qt. In fact, in many situations. The main difference is this. Unlike the others, there is no CPU fallback. This has been built from the ground up with how a GPU that draws triangles works inside. And once you make that assumption, everything you do changes. How you optimize changes. Everything changes. Oops. Oh boy. How do I go back? Very smooth. All right. So how different are the GPU and the CPU? The CPU, generally speaking, does not have any fixed function units. The GPU has a literal metric ton of them. It has samplers, it has a rasterizer, it has triangle setup and clipping. This is very different. So on a GPU, you want to filter your image. Your sampler has fixed function hardware to do it for you. The power efficiency of a fixed function part versus a programmable part is embarrassing. Many, many times faster and many, many times more efficient. What about a rasterizer? Here, this is totally different too. You do CPU rendering, you draw scan lines. It's natural. Your image is scanline major. Natural way to do lots of rendering is scanline. One scanline at a time, and you have your spans. In fact, it's embedded in libFreetype. There's an interface in FreeType so that you can have it export the scanlines for you, or the spans. GPU does not draw scanlines. It draws triangles. And the rasterizer is set up to draw triangles. There's a bit of a difference. What is being drawn then? Typically, the rasterizers work in 2x2 blocks at a minimum resolution. And there's a reason why. It's in order to be able to do texture filtering later. But you're not doing lines anymore. The other thing that's important about the rasterizer is that a GPU can push out a lot more rasterized pixels per clock than a CPU can do in several clock cycles. Okay? And the rasterizers are actually not very big pieces of sand either. And triangle setup and clipping is the name is to feed the rasterizer triangle. And triangle setup is not a pleasant operation. Now this might sound like a joke, but when you do triangle setup, you have to divide. That's got to be one of the most expensive operations to ask anything to do. Division is expensive. All right, so that's fixed function stuff. There's even more in a GPU, but we'll talk about maybe later. What about threads? How many pixels can we handle per thread, or how many thingies can we handle per thread? So if you're really into this, so each virtual core, you have a virtual core in your CPU, and typically with hyper-threading, you have 2 virtual cores per real core. How many registers do you have per core? Not a lot. And when you switch threads within a virtual core, that's an exceedingly expensive operation. All the registers have to be copied out and read into the new thread. And how wide can you make a thread? So if you're into SSE, which is not the easiest thing to write, you can get 4 wide. And if you go full hog AVX, you can get 8 wide, which is really wide. What about on a GPU? So keep in mind, I'm talking about Ivy Bridge. It's an integrated solution, which is very cheap, very power efficient in some ways. So the way GPUs work is every core has so much register space per thread. In the GPU core, switching threads is for free almost. And you have a metric ton of register space per thread. How wide are the threads? So again, taking this Ivy Bridge device, which is several years old already, there are 16 execution units, and each execution unit holds 7 threads. that you can switch through freely. And each thread is 8 or 16 wide. That's an incredible amount of more throughput. And this threading stuff is important. GPUs use threads to hide memory latency when you want to read and write. This is one of the big tricks in GPU design. So that's just kind of repeating about these function parts are really important to use. The one that I also want to emphasize, the depth buffer, is really important too. Very important. And since I'm building something that's designed to use a GPU from the ground up, I'm going to try to use these parts as much as possible from the ground up. But there's a problem. GPUs, like I said, are made for throughput, and changing the state of a GPU really pisses the whole thing off. Depending on what state changed, you might have a stall in your pipeline, or God forbid, a pipeline flush. You get pipeline flushes even when you don't call GL flush. Okay? And at the very least, the stalls are problematic. Sending all the data to change the state is a hassle. It gets heavy. Even when you use something like Vulkan, which is very, very, very low overhead interface, you still have issues. And you do not want to be thrashing between state changes for small jobs of work. If you only got a handful of vertices covering like 50 pixels, you better not have a state change to do them. So, I try to make the stupid thing have one single pipeline state, and I stress the word try. Okay? So what do we have now? We got 3x3 transformation matrix, and this is actually important. This is what Skia has, this is what Qt has. And it's kind of like, and this is also what the W3C canvas has. So that is a requirement nowadays. 2x2 matrix with a translation is not enough for some of the needs in the future. Standard stuff for brush. We can do image, we can do gradients, we can do a transformation on the brush. And with the images, we can do no filtering by linear, which is not surprising, and also by cubic. And we can do stroking pads with and without anti-aliasing. We can do filling of pads, clip in, clip out, and the 12 bordered off modes. And the other nasty blend modes that come in the W3C are not implemented yet, but are on my to-do list. Then there's some other funny features I added. You can do custom shaders for your stuff if you want to do really weird special effects, which is a standard thing that people do for GPUs. And there's this funny feature I figured out how to do where I can do a stroking width, but you specify the width in pixels rather than local coordinates, even if you have a transformation with high skew. And like I said aims to have. Although there are 12 bordered off modes, I need 3 blend modes to do them all. When I get around to doing a W3C, which I plan to do soon, for some hardware, I don't need blend modes. I'm going to do a different trick, and my pipeline state number will reduce back to 1. But certain features that I want landed, they're in progress for Mesa. And once those features land, then I can do this, even on Ivy Bridge. What does an API trace of FastUI Draw look like? It's really unilluminating. You see map buffer, then the application fills the buffer with data, then you see unmap buffer, repeats a couple of times. And I really mean just a couple. Well, not 2, but if you have a lot of loads, maybe 10, 5. Then you see a big thing that sets the GL API set, program, texture, samplers. And then you don't see the API state set almost ever again. You see repeat a few times, bind a vertex array object, bind a texture buffer object, and then repeat a few times, set your blend mode, and multi-draw elements, or draw elements for API doesn't support it. And I think I lost the slide. Oh well. Anyways, this the way this is done, of course, is you have an Uber shader. Okay. Now I work for Intel, and I'm mostly concerned with Intel hardware. I'm not saying I don't care about other hardware like NVIDIA, AMD, or various mobile solutions, but it's the place where this starts. And usually Uber shaders are bad luck. Okay. But there's a couple of differences about what's going on. We're guaranteed in our Uber shader that within a triangle is the exact same path, is the exact same element within the Uber shader. On Intel hardware, all fragments within a pixel shader run come from the same triangle. So there is no divergent branching in the fragment shader, actually. And the vertex shader, I'm not really upset about it because we don't push that many vertices, even on heavy load. We don't push millions of vertices on the screen, but we do push millions of pixels. So what kind of buffers do we have? There's just 3 buffers running around. There's an attribute buffer, an index buffer, and a data store buffer. And the idea is this. Something at a previous time computed the attribute and indexes that you need to push in, and this data is saved. Those values are copied into the attribute and index buffers. Index values are adjusted because they're not copied in the same place they started. And then extra data is put on this data store buffer, which is a small amount of data. And the best way to look at it is attributes and indices are what to draw, and the data on the data store buffer is how to draw. What's your transformation? What's your shader? What's the properties of the brush? And this is kind of like the high-level architecture with no interesting details. The front end is Painter, very classic interface. Then underneath there's a thing called a Painter Packer. And the thing is, what Painter does is it handles a few things that are irritating to handle, and it has data ready. Painter Packer, its job is to copy the attribute index data and do the right thing of putting data on the data buffer store. Then it pushes the data off to the Painter backend, which has to somehow get that data to the GPU API. A backend also has to do other things to storing image, glyph, and other data that come up. No, that's not the right button to push. What does the data store buffer look like? So this is kind of tricky. So there's an extra attribute that's added, which is the location in the data store buffer of where your header is. And the header is several numbers. The unnormalized depth value, we'll talk about that later, what it's for. Your brush, blend, and item shader IDs. Your offset to your 3x3 transformation. Your offset to your 4 clipping equations. And your offset for your brush data and your item shader data. Well, what a shader has to do then, it has to read the data store buffer at the location, get the numbers, and unpack the data there. Okay? Now, how the data is packed is specified by the main part of the library. So on paper, assuming the thing is stabilized enough for its interface, you can write a different backend. And I'm toying with the idea of making a Vulkan backend. And this thing also builds on Windows. Cross-platform support is very important to me. It helps me find bugs and deal with issues. This builds on Microsoft Windows with MinGW and MSys2. So the really sadistic could make a DirectX backend. I don't suggest it. Now, one of the things that comes up is recomputation of data. And this is important. You don't want to recompute that which you already computed. And the idea is what you're going to draw, unless you change it, is computed once to be reused repeatedly. The how to draw, like I said before, is a small amount of data. It's your brush, it's your position transformation, it's your clipping, it's your stroking parameters. And the idea is that this data is more or less orthogonal. So one of the things I spent too much time on is dealing with stroking, where I can change the stroking parameters freely without changing the attribute data at all, including the stroking width. The interface for Painter is organized in such a way that you should not be in a situation where it's not natural to reuse your data. So there's stroke paths and things like this, and you pass the path and it automatically reuses the data for you. For text, there's an idea if you pack up your data of how you're going to draw your text. And how to draw is data that lands in the data store buffer, like I said before. So I guess this is kind of like an example. I already talked about the path stroking, where I can change stroking width, meter limit. Dash pattern is not fully yet implemented, and that which is implemented needs some love still. Another example is path filling. So paths are triangulated, which is an expensive operation. But you only have to do it once you've triangulated your path. And it's set up so that it's broken into its winding number components. So if you want to fill against an arbitrary fill rule, it's very cheap now. You triangulate it once, you know the allocation, the indices, and attributes for that fill rule. But life is hard. What about images? Typical scene, like in a browser, not only do you have many images, they're usually all different. And typically for a GPU API, the image is embodying the idea of what we call a texture. And changing what texture you're going to use changes the portion of your pipeline state and breaks your draw call. And, you know, it's okay to have multiple draw calls in a scene. The issue is you need to have enough work between your state changes and between your draw calls to keep it busy. It's not the number of draw calls. It's how much work between them. This is important. And the problem with UI scenes is that typically if you have a dedicated shader and a dedicated texture for everything, there's almost no work between your state changes. So I say, all right, there's only going to be one texture. And actually, this is not a fully original solution. I first saw this solution when I went to SIGGRAPH several years ago. There's some additions I've made to it, and it'll smell like some game company solution too. So what we do is I break an image into tiles. All the tiles are always the same size. The size is specified at startup. You can't change it for the lifetime of your application, but it is programmable. So now what happens if you add or remove an image, it's just a question if you have enough tiles to fit it in. So you don't have this awful geometric problem of a traditional texture atlas where you have enough bytes free on your texture, but you can't fit the bloody thing in continuously. Okay? There also you have an index tile, which tells you which color tile you have to use. And the index tile can be hierarchical, so you can have images of arbitrary size. So you could have something stupid like 32 by 32,000. Don't, okay? Because that's just dumb. But you could. And the other thing that goes on is that the color tiles, when we break it into tiles, we add some padding. So you can use a GPU sampler to do bilinear filtering. And then there's a trick in GPU gems where you can use your filter, where you can do 4 bilinear filter lookups and then 2 mixes, and you get bicubic filtering. And it's a very nice GPU solution. So this is what it looks like. This is taken from my favorite thing to grab small image data from, Blob Wars. And I took it from the cutscenes, which means I didn't grab small image data. The blue lines are the tile boundaries. And you can see everything's all futzed up. Okay? Now, it's another problem. And this one's a real pain. Clipping. Now, for those that are for those that have experience with WebKit or Blink, or have written or write these 2D renderers, you know that if you want to clip out against anything besides a screen-aligned rectangle, you hate the user. Okay? In FastUI Draw, I don't care what you clip out against, you're going to get the same performance. Good, not bad. And the idea is you're going to use the GPU to handle all clipping for us. Now there is one little caveat. I only support clip in and clip out. 2 reasons why. Number 1, that's all you need for W3C Canvas, and that's all you need for a web browser. Number 2, the other ones, I don't think they're used often, and the engineering pain to implement it is very, very uncomfortable. So how do we do it? How do we make the GPU clip for us and make sure the CPU doesn't do anything? Very important. Make the CPU do as little as possible. So first thing that's very different, I do not track the clipping region at all. So in many UI renderers, clipping region is realized as an array of screen-aligned rectangles that are disjoint. Now this is really good when you're only clipping against screen-aligned rectangles, then there's not many of them. Very bad if you rotate a rectangle and you clip against it. Very bad if you have an interesting path and you clip in or clip out against it. Then you get a lot of them. But that solution is natural and a good solution for CPU renderers because you're pushing out span lines. And it's easy to clip a span line against a bunch of rectangles. So it's a natural solution. But it's a terrible solution if you're targeting the GPU. So how do we clip out? So how do we do clipping? So first I'm going to describe how to clip out because it's the easiest one to describe. So the depth buffer is used to clip out. So what we do is the path by which we're going to clip out is drawn before that which it clips. But the depth value for it is not assigned until after that which is eclipsed has been finished being queued up. And then we set the depth value to be in front of it. So what we get? The depth buffer will now do my clipping for me for clip out. Worse, it gets better. This will actually improve performance because now those fragments, early z-test, can be avoided to be spawned at all. And with a little bit more, there's typically hierarchical z on many platforms, which means you don't even have to check every pixel to do clipping. So actually clipping will actually improve performance, which is kind of counterintuitive. First, when you think, you see a 2D render, clip, that'll improve performance, I draw less. Then you go, oh yeah, because all this goes on. So now I don't clip, so I prefer to get better. And now I'm going back to what I naively thought over 20 years ago. What about clip in? And it's very important that I don't care if transformations happen in terms of performance. So first, how do we clip in by a rectangle? So there are two parts to it. First one is when you first set the clip in rectangle, we're going to use hardware clip planes, which are done by the hardware in triangle setup and clipping. And that's 4 clip planes. Well, what happens if you clip in after doing rotate? Kevin, you're doomed. Because you don't have 8 and then 12 and then 16. And I go, nah. What we do is now we set the clip-in equations to your new rectangle, but now we draw occluders from the boundary edge of the old clipping rectangle. So we still keep the clip out, and we're again using the depth buffer. So what happens is this clipping here, I got 4 quads to draw. I want to clip in against the path, I just have to draw the triangles of the path. Or clip out against the path. And what about clip in against the path? Well, now we clip in by the rectangle of the bounding box of the filled path, and then we clip out by the complement of the fill rule, which is another reason why I wanted to support those other fill rules. Now, for what it's worth, Skia supports the other ones as well. It doesn't just do non-zero and odd-even, it also supports their complements. So what's current state? So most canvas features are ready. Transformations, brush, stroking with or without anti-aliasing, filling with arbitrary rule, clip in by path or rectangle, clip out by path, and GPU glyph rendering. I want to say a few moments about this. Now, when you have a low pixel density device, when you render glyphs and you use a coverage font like generated by FreeType, this is fine for low resolution devices. Not low resolution, but I should say low pixel density devices, like my laptop. It's a huge screen, 19 by 1080, and even huger up there. But when you have high pixel density devices, a single glyph is a lot more pixels now. And storing a coverage font for those kind of glyphs is very bad for memory utilization because it's actually a lot of data. Worse, once you hit high enough pixel density, the hinting on your fonts doesn't matter anymore. And you can start doing GPU glyph rendering. Now the glyph renderer I have here is not the same as Glyphy, and it's not distance field texture lookup, which is terrible render quality. It's another solution I made years ago. It has performance advantages. It doesn't branch anywhere. But, or almost doesn't branch, I should say. It has an early out. But for some glyphs, it renders incorrectly, and I have to write another glyph render. And I have 2 options. I can import Glyphy and modify it severely for how I want to render to make a better shader and better data lookup. And I have another idea which I'm on the fence about, but it's going to take over a month to write. What else is missing? So anti-aliasing for filling paths. So I don't want to result to MSAA to do anti-aliasing. That's just dumb. I want my shader to help me compute a coverage value, an alpha value that I can feed. And I do that for stroking really well. For filling pads, I have two solutions. There's the hacky solution that'll work, probably, and there's the hard solution that's guaranteed to work. The hacky solution is really simple. I look at all the components that I need to that I'm drawing, and I stroke the boundary with anti-aliasing with 1 pixel underneath after I've drawn the filled path. And this will give me anti-aliasing. That's the hack solution. And there is an issue with it that can bite me later. The correct solution is trickier, but it means that when I fill the path, I can do an anti-alias computation, but I need to do a little tessellating on the path. And those that are interested, I'm happy to draw pictures. The other problem with this thing is that it still is not ready. It needs to be productized. Some of the APIs are changing. Some of the enumerations are changing as I experiment with the thing. Anyways, though, I would really love it for people to try it out and give me some feedback. It's been on GitHub for several months now, maybe even half a year. I'm not too sure, but for quite some time. I've made an effort that every class and every function in a public header file has doxy tags. So you should be able to make docs and be able to at least get an overly detailed view of what's going on. There's a bunch of demos, some better than others. You can even do make install. There's some scripts so you can use it in your projects. And of course, you can give me some feedback either through GitHub or in my email. Oh man. Demos? Sure. Where's my mouse? All right, so let's take a look at the Painter Cell demo. Please work correctly. So I don't know how this thing's going to freak out. It works! Okay, so let's take a look at this demo. And there's a lot of things going on. So we have a very high frame rate. Now I'm going to make a confession. In spite of all the effort I do for GPU stuff, I'm still CPU bound. Believe it or not. I look at Intel GPU top, render busy is not at 100%. And there are reasons why. I have one idea how to deal with it, but I really don't want to write it. Anyways, let's pause it. So there are a couple of things that's important to me. So here we go. We see the text, nicely anti-aliased, and we can zoom in freely. The text is not a coverage font. It's a GPU rendered text. This is important because if it was a coverage font, as I would change resolution, attributed index data would have to be recomputed every frame as we zoom in and out. Really important for it to be GPU rendered to keep the data more static. Now every cell, I don't know how to use my laptop obviously, we have rotating here. And so people will comment potentially on the alias jaggies on the boundary of the cell. I don't know if you can see it, but it's there. Yeah, you can see it quite clearly. Okay? But on the interior of a cell, you don't see aliasing jaggies. And the reason why is clipping causes aliasing, but stroking does not. Okay? For what it's worth, two of the renderers I played with on GL, both Skia and Qt, they exhibit the same problem. Clipping causes aliasing on the GL backends, but stroking does not. So let's turn off the rotations. Let's take a look at a few other things here. So anti-aliasing to me is very important for stroking. And this one there. And here, you can see here I haven't retessellated yet. I need to write more code to tessellate based off the transformation and save those tessellations. But what's important here is that that's anti-aliased, and we can draw it without. Now you can see the jaggies on the boundary too. And if you want, we can take a look at the other toolkits running it too. So let's take a look. Let's see how well Qt runs. So this is the GL backend for Qt. It's about 1/10 the speed. Worse. Now, I saw an article about me on Phoronix, about this on Phoronix, and some of the comments were really wrong. Let's take a look at the text on the Qt. Now you notice as we zoom in more, performance increases because there's less to throw at it and gets less confused. You see how the text is starting? It looks good. Now what's going to happen is, as I zoom in, it's going to be blurry, and now it's going to transition to alias, although this is not doing what I want it to do to show you. Ah! And now I'm a liar. Well, anyways. So for Qt, for those that are into how Qt's GL backend works, it does some interesting things. On the Qt GL backend, it uses a glyph cache to render the glyphs until there's too much zooming in or out on your transformation matrix, and then it'll render the glyph as a path. And you can see the aliasing effect, just apparently not on the projector right now, and which is really funny. I should be able to get it up for you, but I'm not doing a good job now. Anyways, that's about what I have. You guys want to see the Skia one run as well? All right. So I will admit, getting Skia to build and cooperate with me requires significant effort. And Skia is faster than Qt. About Did it do something? Thanks, Martin. So the Skia backend has really good render quality, and you can see the jaggies on the boundary of the cells for clipping too. But I apparently don't know what I'm doing with the microphone. I have my entourage helping me.
Oh,
I'm like a movie star. I can't do anything myself. But this is the kind of state we have. And the goal of this thing is to leverage the GPU as almost as much as possible and to open the door of really hard scenes to draw. I'm tempted to add to the painter cells of occluding by a path, a filled path at the front of it, and see how badly or well they all perform. The awful part is fast UI draw's performance would improve. All right, but that's all. I think I've almost finished on time. So, questions, flames, amusing comments? Yeah.
So I guess for the images you had this atlasing solution. It's probably from the game industry, so using the sparse virtual texture tricks.
That's incorrect. It's not sparse virtual texture. So you're probably thinking of its software's technology with their mega texture, right?
Something like that.
So it's kind of like that, but I'm not. So what they have is much more than what I'm doing. So their main issue with IdTech mega texture is the following. They want to be able to stream in textures. So what they do in there is that you have a frame run on the IdTech engine, and it's not there, but a low resolution bitmap level is. And then usually the shader triggers off some data to be sent off to be loaded up. I'm not doing anything like that. You create an image, the image data is statically put on there. You delete an image, the image data is taken off. So it's much more simpler. But it does smell like it. You have these tiles, you have these index tiles. There's one little addition which is useless for games, but very useful for web browsing that I have as well, is that if a tile is the same color, it's tagged. And if you have another tile of the exact same color, all the same color, then what happens is you don't replicate the tiles. And it seems like an odd optimization until you look at the junk that web pages send web browsers. Very often web pages, they'll group all their images into a single PNG, or many of them. And the PNG is loaded with a bunch of empty space. Now it's perfectly fine when you're transmitting the data and it's compressed. Complete disaster if you can put all that data onto a single texture. But now, since those empty tiles, that empty space, all zeros, is only stored once. And this is a big deal, actually, if you think about web browsing stuff. Now, the other confession I want to make is the tiling thing I have there is not my first choice for handling textures. The truth is, my first choice for handling textures would be an interface called bindless texture. But on the Intel side, the hardware capability is only really in Skylake and up, and that's kind of, depending on your point of view of purity, might be an issue. It's not in Gen 7 or 8 or 7.5. For NVIDIA, it started in not their Fermi, but the next, no, it started, what was their first DirectX 10 name? DirectX 11 cards, the ones that,
Kepler,
the 400, yeah, so it's not in Fermi, but it's in Kepler, the newer ones. And for AMD, I haven't looked at what the support is. But also on the side, for open source drivers, the interface is not yet implemented. And it seems a little to me like pushing the luck. But I would prefer bindless texture. I wouldn't need to do the slack. And it would simplify, the other thing I don't like about the tiling texture is that it complicates my fragment shader, because I have to walk down the index tile hierarchy. So if I have just one index tile, I need 2 texture lookups within the fragment shader, although the first one is heavily cached, so it's probably not a big deal in terms of memory bandwidth. But it's an extra texture lookup. That's more cycles in the EU. And if I have 2 levels of index tiles, that's 2 texture lookups. But the index tiles should stay in cache for the lifetime where the image is being used. But I would much rather do bindless texture. But
yeah, I was about to
I'd rather have a Porsche as well.
I was about to suggest the Vulkan or OpenGL sparse textures, which would be sort of allocating a big texture, but not
and then you do it, and
attached physical memory resources
as
needed.
You could do that way. So that would be the old style texture atlas with sparse. The advantage of doing that is then you just space it by 2. MIP mapping's a little icky. You're going to have to pay attention to boundaries. I don't support MIP mapping anyway, so I'm lying. For the sparse texture, you need to pay attention to your boundaries of when you spoon stuff in and out.
And then there's also the issue.
The main advantage of sparse is if you don't need to have everything resident at all times, and with this, like, it all still needs to be there at all times. Is the difference, right? So like with the it's the mega texture problem, right? You've got this giant huge world, but you can only see some tiny little bit of it, so you just say, you know what, don't page in the stuff that's on the other side of the city because I can't see that, and so it doesn't have to be there. But with something like this, all of the stuff just needs to be there. It's how do you pack it in and make it available and not have 47,000 little tiny textures, because you can only have 32.
Yeah, but the thing he's thinking is like this. You have one very large texture, very large sparse texture. Let's make the number ridiculous, 64 million by 64 million. And then you no longer have the geometry problem of putting in your textures into this virtual sparse texture. But it's still not tricky. It's still not pleasant to deal with. You still have to track your geometry to put things in and out. And you still have the same problem you did before. It's just larger now. And I would not do sparse texture. I would either prefer bindless or what I have now. And the other thing with sparse texture, you do run a danger that you're going to allocate more memory than you can have. This one says, look, here's the finite size of the texture. You can't fit an image here. Image creation fails. You do something now.
I guess sparse texture would help that you could allocate one giant texture, say 16 by 16K, but not have to put in the physical memory in there.
Yeah. You wouldn't do 16K. You would do a texture array, 16K by 16K by 16K.
By 2K is the maximum. So that would be 512 gigapixels.
Yeah,
that's plenty.
Yeah, but the idea is you still have the geometry problem. You have to fit your textures in. You have to track it. And you have to be able to pull it out. You may not worry about, well, I don't have to worry anymore about it because I have such a big texture. And then someone's going to turn around like me and make a stress test and fry it. And I really don't like the sparse texture solution. It's something I considered, and I go, no.
Thanks.
Any other question?
Have you considered porting your benchmarks to Android hardware accelerated 2D?
That's Skia.
No?
Android draws with Skia.
No, hardware accelerated 2D, it does not use the GL Skia backend.
What does it use?
They have their own acceleration architecture. Either you draw with CPU or then there's a...
Okay, because I always thought Android drew with
That would
Skia.
be an interesting reference because...
Yeah, it would be good.
Because Skia backend just implements the drawing with GPU, but doesn't do any optimization as far as I know.
I wouldn't say Skia doesn't do optimization. What happens
Well,
is,
but if you just draw simple primitives and keep on drawing whatever you do with CPU rendering and just translate that to GPU, it's not the most efficient approach.
Yeah.
And the hardware acceleration in Android does something more clever. I can't describe that in detail right now, but...
we should talk.
Yeah,
after.
maybe.
But to answer your question, obviously I didn't because I didn't know better. I just thought Android always used Skia. I didn't know that the GPU backend did not. But I should, but I hate writing native Android code.
Yeah, it's more work to port it to Android.
It's awful.
Okay. Well, thank you. Thank you, Kevin.
All right, are we ready to start? Hello? Maybe I'll just start. So, hi, I'm Rob Clark from Red Hat, and I'm going to talk today a little bit about some tricks for getting more FPS, some driver tricks for getting more FPS on Tyler GPUs. And I also do a lot of work on Fredrino, although a lot is applicable to other Tyler GPUs. So the problem statement is basically this. Tiling GPUs optimize memory bandwidth by doing as much rendering as possible with the depth stencil and color buffers in an internal tile buffer of some sort in internal memory inside the GPU core. But the problem is many things that GL apps do, especially ones that are written more with desktop GPUs in mind, trigger unnecessary flush and resolve, meaning move the contents of the tile buffer back to system memory and then later move it back from system memory into the tile buffer. But there's some tricks a GL driver can do to improve this, including batch reordering, or what Eric calls job reshuffling, and also resource shadowing, and some people call that ghosting. And this is hopefully the sort of thing a driver would never have to do in a brave new Vulkan world, but for a GL driver, we kind of have to do this. So I'm going to try and give a really simple example with this hypothetical awesome FPS game called Triangle Quad. I think a lot of people have a good idea how normal non-Tyler GPUs work, but don't really think about the implications of how a Tyler GPU works. So I'm going to first try and explain this simply. So with a traditional GPU, on the bottom you see basically the command stream, the top color buffer. So normal GPU, first thing you do, clear, then you draw a quad, and you draw a triangle. Okay, that's simple enough. So a Tyler GPU, though, does this per tile. So clear, quad, triangle, and again for the next tile, and so on. But the important thing to notice is it's executing the command stream for each tile. And different tilers are different. Most of them actually tend to use something between 16 by 16 to 64 by 64 tiles. Adreno has some flexibility with various different tile dimensions. That's not really important at all for the purpose of this talk. So now, first, what if this game is doing something that causes problems? So since this is a super modern game, it's actually using a uniform buffer object, a UBO, to pass the color to the fragment shader. I mean, this is not what you'd really do, but just bear with me. And this is really the exact same scenario for a game that does a texture upload mid-frame, for example. Typically, the way a non-Tyler GPU would deal with this is by using a staging buffer. So when it sees, to avoid flushing rendering, when it sees an update mid-frame to a buffer, it will allocate a small staging buffer on the side. So in this example, you see the UBO and the staging buffer with the new color. And the command stream would look like something like clear, draw the quad, copy the staging to the UBO, or upload the new texture and generate bitmaps or so on. I mean, it's really all the same problem. And then draw the triangle with the new quad. But that doesn't work out so well with a Tyler, because since the first draw for the next tile happens after the last draw for the last tile, even if you could hypothetically do a unrelated DMA mid-tile pass, you'd end up with something like this when you get to the second tile, because you already have the new contents in the UBO. So a Tyler ends up needing to create two versions of this buffer, the old and the new version, or shadowing the buffer, or ghosting the buffer. in order to keep around both the old and the new copy, so that when you get to the next tile, the first draw sees the old copy, next draw sees the new copy. So without doing something like this, a tiler driver would be forced to flush after the first draw, moving all the contents of your render target back to main memory. So for simple example, 32-bit RGB8 at 1080p plus depth and stencil, that adds up to 16 megs right there. And that can easily go up if you're using, you know, float 16 or float 32 per component formats, if you're doing MRT with multiple render targets, and so on. And then each of this unnecessary flushes you end up doing is going to involve later moving that data back into the tile buffer. So, okay, you got 16 megs writing back to memory, and then later 16 megs of bandwidth to pull it all back into the tile buffer. And you kind of want to avoid that. So, the dirty tricks the driver ends up having to do. You end up needing to shadow UBO UBOs for UBO updates, textures for new texture uploads, and so on. And the semi-related, let's say, cousin of this problem is unnecessary FBO switches. Like an app might create multiple FBOs, clear one, switch to another, clear that, switch back to the first. It's really all the same problem. It ends up needing extra resolve passes to move tile data to memory and restore passes to move it back into tile buffer. So because, at least in the case of Ferdrino, we use ublitter to do all these blit transfers, including things like bitmap generation when you upload a new texture. So basically, every mid-frame update of something ends up looking like an FBO switch. So, yeah. Fortunately, because of this, if we handle solving the FBO switch case, we handle mid and plus a little bit of logic to shadow buffers, we've kind of solved both problems together. So the first thing to solve is actually split out a batch object. And VC4 calls this a job. I think Vulkan calls it a tile pass, or maybe a sub pass. Basically what this is something that tracks all the command stream related to a single pass of n draws of data while it's in the tile buffer. Also ends up keeping track of some auxiliary data, like we need to know if the previous contents were cleared as the first operation. Like, for example, if there's a GL clear as the first thing, we know we don't have to pull old data back from memory before the clear. In the case of Ferdrino, Adreno can actually work both in tiling and non-tiling mode. Non-tiling mode, bypass mode has some restrictions, so we keep track of, whether blend was enabled, whether depth stencil was enabled, and how many draws, and that lets us decide actually whether we're going to do tiling or not. There's some tricks like if scissor is used, we kind of accumulate the maximal scissor area over all the draws and skip out all of the parts of the render target that are scissored out for all of the draws, which lets us skip a bunch of tiles for typical UI type workload. And we also have, when you add queries into the mix, we have to keep track of query result buffers per batch. So the batch is a basic, and also per batch. Since Adreno, we have to build up command stream to explicitly move stuff into tile buffer, jump to the draw commands, and then move stuff back out of the tile buffer. So the tiling part of the tiler is handled explicitly. Other GPUs might do that more automatically, but that's part of the batch object. now that we have a batch object, we have a batch cache. So we keep track of however many batches. We map from the render target state, which in Gallium is the pipe frame buffer state. That includes your N render target, multi-render target color buffers, plus your depth stencil buffer. Whenever there's an FBO switch or a set pipe frame or set frame buffer state call in Gallium, we hash from the pipe frame buffer state into the hash table and look up batch and see if there's already some rendering we've accumulated for that combination of render target buffers. Otherwise, we create a new one and add it to the table. Now, if we start reordering things, we end up needing to do a lot of dependency tracking. For example, you could have some render commands that write data into a texture, and then other render target commands that sample from that texture, and obviously we can't change the order there, or you'd get incorrect results. So per resource or per buffer, we end up needing to track n batches that read the resource, plus up to one batch that writes to the resource. Per draw, we need to look at all of the bound objects to see, what the state of various resources that are read and written. So for example, textures are read, UBOs and VBOs are read, transform feedback buffers are written, query result buffers are written, so on. And obviously depth stencil and color buffers are written. For resources that are written by the draw, dependency on other batches that read or write. If it's written, anything that reads from it needs to go first. And then now obviously anything that writes to it needs to go first. Resources that are read by the draw, I actually spelled that wrong, depend on previous batches that write to the resource. So that we kind of figure out a dependency structure between, we use that to build up a dependency structure between the batches so we know what order the batches need to execute. And also not just GPU access, but CPU access, like anything that does a write pixels, we need to flush out any GPU operation that reads from the buffer and have that finished before the CPU can write into it. And vice versa, and similar for something that reads, which is mainly Piglet and stuff that does GL read pixels. So, but I wanted to try and keep this overhead not too much, cause, on the I didn't want to have too much CPU overhead in all of this tracking, because I didn't want to penalize things that are written well from the point of view of how a tiler works. So the first try, I just kept track of a single last read batch, and multiple batches or multiple reads in a row just end up building up a linked list plus a last write batch. But turns out with the way uBlitter does MIPMAP generation for multiple MIPMAP levels, that ended up introducing fake read after write dependencies, which we ended up flushing in places where we wouldn't otherwise need to. So doing it properly kind of meant, okay, well, a hash set of dependent batches per batch, plus a hash set of read or written resources per batch, plus per resource, per buffer, a hash set of batches that read the resource, plus a batch that writes the resource. And yeah, hash sets are constant order, but kind of bigger than I wanted constant order. Plus, it's a lot of extra memory allocation going on. I mean, you could have hundreds or thousands of resources and hundreds, thousands, many hundreds or more draws per frame. So what I kind of thought is, well, actually, max 32 batches in flight at a time would be reasonable. I mean, anyways when a game or a level is starting up and it's doing a lot of texture uploads and stuff like that. We don't want to defer all of that until the first frame gets rendered. And the 2 batches end up being enough for more than 2 times the max number of bitmap levels, which turns out to be kind of useful. The reason that's useful is uBlitter ends up generating a batch per bitmap level that it generates. So when we do resource shadowing, we end up having to copy or potentially copy old data from the old resource into the new copy of the resource. What ends up happening is I generate back blits for each level of the resource. And then later, if I get a real blit to say, like from the GL API level, we don't know if the immediate next thing the app is going to do after it uploads new texture data is generate bitmap levels. So we have to pessimistically generate these backblits and cache them. And then when generate bitmap gets called, we say, oh, we can throw that away and do a real blit. So being able to cache at least more than the number of levels you need to generate bitmaps turns out to be useful. Anyways, the nice thing about limiting it to 32 is it turns a lot of this hash table stuff into bitmask operations. So insert becomes an or equal. Test for whether something's in the set becomes an and. Remove becomes an and equal not. And iterate is just calling FFS in a loop to find the first bit set and then clearing it. So that kind of makes basically all the hash sets go away. So except for one, and that one could go away. We end up having to keep per batch the hash set of resources, although we avoid most of the hash table lookups by testing the resource batch mask bitmap against the batch index. Merging the libdrm levels in the Gallium driver, like VC4 does, could probably get rid of that hash set, but that has some other problems. Yeah, so anyways, the results are, so SuperTuxKart with the new render engine was up about 30% because in that case it was doing mid-frame UBO updates. So shadowing those and skipping the restore resolve a couple times was a pretty good thing. Manhattan was doing mid-frame texture uploads. Avoiding those was worth, another 20% FPS. I didn't really initially look too much at GLMark, but actually Eric pointed out that some of them benefited too, and turned out the GLMark desktop blur test picked up 7%, and the GLMark shadow benchmark picked up 20%. I didn't really look too closely at why in those cases. Anyways, I kind of ran through that fast, but questions? Uh-huh. Mm-hmm.
I'll repeat for the record. So when you shadow the resources, do you do actual copies, or are there a way to do page table tricks so that you don't actually have to use the bandwidth to copy?
In very special cases, you could potentially, but I mean, it's really about the GPU page table and not the ARM CPU page table. And also, I mean, there's really two cases I've focused on so far for the resource shadowing. and that is a UBO update, which is usually a small amount of data in a relatively small buffer, but not really aligned to page size.
Yeah, so that doesn't matter.
So that doesn't really matter. And it's something that's usually safe to copy with a mem copy because it's not pending a GPU write usually. The other case is texture upload, and what I've seen usually happens is you at least upload the whole first level. So you're not doing like a GL subpix. And in that case, the question is whether you need to copy all the remaining levels or not. If the application immediately uploads itself all the remaining levels, you can throw away the backblit and not really do anything. You end up the same amount of mem copy bandwidth in either case.
Yeah.
If not, then it's probably going to call generate bitmap because you usually don't want the old lower bitmap level contents with the new first level, in which case it's the GPU doing the copies. But usually nothing ends up being page aligned, so yeah,
it's hosed anyway.
Yeah.
Another question is, and I don't, what about for stuff where image loads store where shaders have side effects?
So in that case, I mean, you'd basically assume the buffer is written by the draw operation. I mean, in a sense, it's the same thing as transform feedback, except for it might, except for in the case transform feedback, it hasn't written the buffer.
Yeah.
But if you don't have any guarantees that, well, I only differentiate between read only and read write. So write only is not, it doesn't really matter.
Thanks.
Everyone just wants to go and leave, get beers. All right.
Okay, that was the last talk. So I guess the